Morning. I hope that you are feeling well today. Our next speaker is one of the co-organizers of this summer school, spring school, is Abdul Kara from the University of Leeds, and he will talk to us about first integrals and reduction for the Emden and the Lennard equations.
Thank you. So good morning, everyone. As I was telling Stephen, we apologize for the weather. This wasn't expected. So when we were deciding whether it was going to be a summer school or spring school, now you can see, I mean, it rains in Cape Town in winter, so maybe it's a winter school. So expect the worst. Well, it's not that bad, actually. So welcome and thanks for attending. When I chose this topic, my general intention was to direct a lot of the stuff to some of the younger people, the guys who's been just entering this field of symmetries, who may have just finished their PhDs, who are maybe doing their PhDs, and to raise some questions and or some ideas that have sort of been, I think, almost buried for a long time. And Sergey, you will bear testimony to many of the things, because the one thing you mentioned in as a question in one of the talks was about two-dimensional subalgebras and so on for ODEs and so on. So I'm going to talk a lot about second-order ODEs. And a lot of the results have been established, been done a long time ago. And at the end, I'll sort of put in a small aspect to where it applies, or I think it would apply now. It's something sort of new. Okay, so as far as second-order ODEs are concerned, I mean, all the classification was done. It was done a long time ago. When I say long time, at least 25 years ago. So we know that, first of all, the algebras that, or rather the classification of the second-order ODEs are split up in the following way. So second-order ODEs may generate zero symmetry. I'm talking now Lie point symmetries. One symmetry, 2, 3, or 8. Second-order ODEs as a complete algebra do not generate 4, 5, 6, or 7 symmetry algebras. Right. So if they generate, say, three-dimensional algebra, there are various sub-classifications of that. I think there's about 4 classes, or maybe no, 4. That's a bit more. For second-order algebras that they generate, they split into 4 possible classes. So once you know these symmetries, what do you do with them? Well, if they generate 2 symmetries, theoretically, you could reduce them to solutions. One of the things that's done is, of course, to use the symmetries to find some sort of change of variables to cast them or transform them to some standard classified equation. In other words, what did Peter Leach call them? A sort of a known equation, just transform them to those kind of equations. Now, the one I want to focus on quite a bit is the very nice case. So if a second-order ODE generates an 8 parameter algebra, in other words, 8 symmetries, Lie point symmetries, then you are guaranteed, or of course, there's only one class of 8 symmetry algebra that a second-order ODE could generate. It's the SL3R. And if it generates that, you are guaranteed it is linearizable. So it's either linear, which is straightforward, but if it's not linear and it generates an 8-order algebra, it would be linearizable. How you linearize it is another story. I mean, you could use a symmetry, etc., but you're guaranteed that. Now, going on with that, another aspect of, let me stop there for a while. Another aspect of studying second-order differential equations, ODEs, ordinary differential equations, was through the Lagrangian variational picture. There, the pictures are slightly changes in terms of the algebras you generate. So one of the things we know we could do is, if you can construct or find a Lagrangian associated with a given second-order ODE, then the old classic thing to do was to find the Noether symmetries, right? So first of all, you'll use a Killing type equation with gauge, possibly gauge terms in there. You'll find all the Noether symmetries. And what do you do with the Noether symmetries? The standard thing to do would be to construct the first integrals using Noether's theorem. Standard thing to do. It's the kind of thing we do even for PDEs, if you know what a Lagrangian is. Now, how do the symmetry algebra associated with the Lagrangian, the Noether symmetry algebra, compare with the Lie symmetry algebra? And I'm going to focus more on, because it's interesting, on the linearizable or linear case. So the trouble with the Lagrangian picture is that you might not have the best Lagrangian. Lagrangians need not be unique. I mean, you take this, the classic case, the basic case, the free particle equation, y double dash equal to 0. I mean, you could find Lagrangians that are rich in symmetry. When I say symmetry, yeah. When I say Lagrangian, I mean the Noether symmetries. Or they might just generate a few, and sometimes you might end up with a Lagrangian that doesn't generate any symmetry. You want, of course, a Lagrangian that generates at least 2 symmetries, and you can find 2 first integrals, and voila, you can get to finding solutions. In fact, if you have 1 symmetry, you could, of course, go to a solution because your first integral will also be or inherit the Noether symmetry. And then, of course, you can reduce one more time to solution. In particular, when you look at a linearizable or linear equation, you hope that you have a Lagrangian that generates the maximal number of symmetries. Now, in the case of second-order ODEs, what was then regarded as the best Lagrangian is the one that would admit the maximum number of Noether symmetries. And it turns out that the best Lagrangian for second-order ODEs would generate a 5-dimensional algebra. So think about this. On the one hand, the maximum number of symmetries for a linear or linearizable second-order ODE is 8, SL3R. If you went through the Lagrangian route, you'll end up with a symmetry algebra that's 5-dimensional, maximum. And that algebra is the A540. Of course, so the question is why look for a Lagrangian? Well, of course, the whole reason for going the Lagrangian route was it gave you Noether symmetries, which via Noether's theorem gave you first integrals. So that was sort of the classic thing that was done for a long time, the classification. And of course, the old classifications depended on known classification of algebras that you mentioned, done by Patera and Winternitz. And I think prior to that, or maybe, I don't know how much before, Mubarak-Ziyanov was quite Russian, involved in classifying algebras and so on. But the better known one was the classification done by Patera and Winternitz. Later, by the way, Winternitz concentrated more on discrete and difference equations and so on. So, in a sense, when I looked at this, so this particular example, the Emden-Leonard equation, I mean, this is if you've ever worked with Peter Leach or involved with his group, the Emden equation is all over the show. I mean, Kesh Carpenter was quite involved. I'm not sure if you were involved with the Emden equations and so on. Peter Leach was very much involved with the Emden equation. So I don't want to get into the details of where the Emden equation comes from and so on. Of course, it has its place. But Peter Leach was also working with Maria Claranucci in this kind of area, the Emden equations and so on. And what I found is that Maria Claranucci, I mean, I think a lot of you know her if you've been in touch with PUT or UKZN, had worked a lot on second-order ODEs, some with Peter Leach and some with another group. And one of the classes of equations that they looked at was the Emden-Leonard equations, Leonard type equations. And in one of those papers, she very interestedly discussed how one constructs Lagrangians for second-order ODEs. That was all. The problem with the Lagrangian picture was always, how do you find the Lagrangian if you're going to go the Lagrangian route? I mean, there's been lots of papers written on how to construct Lagrangians for ODEs. It was much more difficult to deal with PDEs. There's this classic paper by Anderson and Duchamp, Ian Anderson and Thomas Duchamp, where they discuss construction of Lagrangians for partial differential equations of a particular form. And even then, the problem was, if you had the Lagrangian, the question was, after all that work, do you have a nice Lagrangian? Nice in the sense of, will you be able to, will you get some nice Noether type symmetries or gauge variational symmetries? because that's what you want. Otherwise, why go the Lagrangian route? There might be some physical reason. I mean, physicists always talk about Lagrangians in terms of potential and kinetic energies and so on, something I'm not too familiar with. But usually, as far as we go, the whole idea of Lagrangians was to construct first integrals via variational symmetries. This little work here was initially concentrated on finding or constructing Lagrangians using what they termed as the Lagrange last multiplier. So it's a standard procedure, quite a complex procedure to find these, to construct Lagrangians for second order ODEs, but they focused on example of this particular class of equations. And of course, when they did this, the next step was to say, well, what can you do with a Lagrangian? Well, what do you do with a Lagrangian? You find the symmetries. If you're a symmetry person, and then look to constructing first integrals. And it turns out that various, dependent on the forms of the functions that you will see come up in these equations, you get various cases coming up in terms of different Lagrangians and different algebras they generate and so on. It turns out that you do get certain classes of this Emden-Leonard type equations that generate one symmetry, now back to Lie symmetry, 1, 2, 3, or maybe 8. The nice thing is the following, that if once, and it's a nonlinear equation, is that as soon as it generates 8 Lie symmetries maximum, you have the SL3 algebra, it is linearizable. And like I said, that how you linearize is then another story. So it's really the next step if you're going to go that route. Just as a point of interest, another way, once you know that a second order ODE is linearizable by looking at its Lie algebra of symmetries.
You can use great linear because
Yeah, I'm gonna come to that. Yeah. So one of the things we've done with Faisal a long time ago was to say, well, if an equation is linearizable, we know the standard linear equation is second order ODE is either the free particle equation or maybe the simple harmonic oscillator equation, for which the best Lagrangian is known. So what you do is you map the one Lagrangian to the other using a symmetry. So you use your symmetries to construct the transform variables, and then you have the map from the one equation to the other. And then you can do a whole lot of things with it. You work with your free particle equation or your simple harmonic oscillator equation and then transform back. Okay. That was one. Oh, so just to make the point that Sergey is making, that dependent on the form of certain second order ODEs, you can test for linearizability. So there's a standard theorem. I'm not sure to who that theorem is Lie, that you could test whether a second order ODE is linearizable. Of course, that depends on that particular form of the second order ODE. You don't have to go the symmetry route. That's what it's saying. So you could just plug in these unknown or these the various terms in the function into this standard test. And if it passes the test, it's linearizable. And of course, after that, you know that it's going to have generate 8 Lie symmetries and so on. And then if you wanted the Lagrangian, you hope that you get the best Lagrangian. Whenever I say best Lagrangian for a linearizable equation, I mean the one that generates the maximum number of Noether symmetries, the Lagrangian, which is 5, and which should be the A540 algebra. So, well-known theorem of Noether, everyone knows this. For every Noether symmetry, variational symmetry, one could find a corresponding first integral. That's Noether's theorem. So if your best Lagrangian is going to generate 5 Noether symmetries, then we're going to correspondingly obtain 5 first integrals. Okay, Noether's theorem, of which 2 will be independent, and you may be able to write the others in terms of those 2. Okay. So I'm going to broadly speak about those ideas in the context of this particular example, a set of examples. So now the page is not changing. Why? Oh, okay. So I've spoken about all that. Okay, so the class of Emden-Leonard type equations that Maria and her group looked at and studied over a number of papers, like 3-4 papers, was this class of equations. And they showed various cases of this, the functions, various forms of f of y and g of y that generates the various subcases, those that are linearizable, those that generate maybe three Lie symmetries, etc., etc. And I'll look at them as I go along. But what I'm going to do now is the following, and this is the broad idea, that why go through all the trouble of constructing the Lagrangian? If you're interested in the first integrals, then you go the multiplier route. And usually, I mean, I've noticed that most of the work done in terms of the multiplier method in constructing conservation laws and so on was concentrated on PDEs. And maybe understandably so, because all the work on second order ODEs and so on was done. But you're always going to come up with second order ODEs somewhere, I mean, in reductions and so on. So how about revisiting the second order ODEs, but with a different eye, with a different picture, with a different angle? Maybe the multiplier route. Why take all the trouble of constructing Lagrangian? Because you're going to have two problems, Lagrangians, standard problems. One is constructing the Lagrangian, finding the Lagrangian. I mean, that's a procedure in itself. And then, how are you going to know that you have the best Lagrangian? Again, here best is defined by the number of variational symmetries that Lagrangian will generate. So you could take all the trouble of finding the Lagrangian, and you may end up with a Lagrangian that generates no variational symmetries. It's possible. But the method that, and what you're going to do with the Lagrangian, you usually do the symmetries and first integrals anyway. So how about visiting or revisiting these classes of second order ODEs using the multiplier approach? Because as Stephen said in his talk, I mean, they give you all the first integrals by giving you all the multipliers. So I just looked at those classes of equations again and see what we can do. And there's no talk about Lagrangian. You don't have to use the Lagrange, the Jacobi last, that's what you call it, the Jacobi last multiplier to construct Lagrangians. And I looked at the procedure, and it's quite a hectic set of things you need to go through to construct those Lagrangians. So let's have a look at that again. So broadly, this is what I'm going to look at, but now applied to this class of equations. And this is the various classifications of the functions f and y, f and g was essentially done by Maria and her group.
No, Abdul, initially had been done by Sophus Lie, because this equation, you can remove the function f without problem. You can remove it. So you just have one function, and you have an equation which is c double dot plus a function g of y c equals 0. So the problem solved by Sophus Lie.
So let's look at what Maria did. And so let's put this, yeah, okay.
It is, okay, you continue.
So
you can kill it, the quadratic part. You remove it by point transformation.
okay, so you have only
Just delete the equation of the usual.
no first derivative terms then.
No, you in this case, I can show you.
Okay, one learns something all the
I
time.
mean,
Yeah.
it's a simple transformation. You just define y to be x of the function of the integral of f, dy to be yes, dz, a new variable z.
Okay.
X in the integral of f dy.
Okay.
You, eliminate.
So, but anyway, let's just suppose that
Yes.
we have this class, because I think they went the Lagrangian route, they've applied to this.
The problem was already solved. I mean,
Okay, that's okay. So again, what I'm saying is the classes are based on what they've done in their paper. Okay. So one of the classes they obtained was this particular class that generates a three parameter Lie algebra of symmetries. These are Lie point symmetries. And again, I mean, I would imagine that if you're going to construct a Lagrangian for that, it's going to be a bit of a task. And the symmetries obtained are, of course, given by x1, x2, and x3, and those are the commutators, etc. And what I was now suggesting is that cut out the Lagrangian root, whatever that involves, right? And let's see what kind of multipliers we obtain, or at least the number of multipliers, and then correspondingly, one could, of course, construct the first integrals. So the multipliers, of course, as was discussed in many talks, are obtained by 3.3. The Euler operator on the multiplier and the product, we is equal to 0 because we want a conserved form there, which is annihilated by the Euler derivative or the Euler operator. I should say Lie derivative. Okay, it turns out after some calculations, whether you do it through Maple or in this case, you could do this by hand because we restricted the multipliers to being of first order. And we end up with these three multipliers, and each of these are then associated with a corresponding first integral. Find the first integral. Yeah.
Didn't you need to make some assumption on the form of the multiplier? Like you're not going to be able to find all of them in that class that you're trying.
So that was the form that was in a sense assumed. And it was by looking at certain things.
Yeah. It's not like Lie symmetries where you can find all.
No, the symmetry was not. Oh, I didn't look at.
You can't find all multipliers of the general form that you wrote down. It's impossible. It requires knowledge of the first integrals. This is all discussed in the Bloom and Anko book.
No, but what I'm saying is
So
the symmetry concept wasn't looked at yet to find the multipliers.
Saying what you said to the audience is just now compute all the multipliers of that general form. And then you wrote this as saying, as if it's simple to do that. I'm saying it's not possible to do that. To find all the multipliers of the general form you wrote down, you would need to know how to integrate the ODE. So by inspection, you might guess a class of multipliers of this form, but it's not a computationally complete problem the way it is, for example, to find all Lie symmetries. Because for Lie symmetries, it's an overdetermined system. It splits. You can just integrate it. It's not the same case for multipliers.
No, I'm not understanding your question. I'm saying this, because the computation of that was done through Maple.
That's not possible. So if you look in the Anko-Blumen book, it's very carefully explained. It's just what you're saying is not possible.
Well, we can have a look at it later because.
Okay, but I'm just saying it's not possible. There's a big difference.
Why do you say that's?
If you assume this is linear in Y prime, then it's possible.
Oh yeah. Okay, so now I see your question. Okay, yes, I've kept this linear in Y prime for the following reason. Yeah.
Restriction.
Yeah, but the reason I kept the restriction on Y prime was the following. If you use, so I had Noether's theorem at the back of my mind, right? If you're going down the Noether's theorem route, you're always going to get first order multipliers because those are the characteristics, right? For ODEs.
If you're using Lie point symmetries for Noether, but you could use contact symmetries or dynamic symmetries. There's lots of examples of that.
I'm not using contact symmetries.
But you could.
We could, but that's not what I'm doing. I'm concentrating on Lie point symmetries or point symmetries.
What you want to say to the audience is you're going to look for multipliers that are analogs of Lie point symmetries.
Okay, so I agree that the reason this was restricted to first order multipliers, first order derivatives, because that is what Noether's theorem mimics. If you're going to construct first integrals via Noether's theorem, then your multipliers are necessarily going to be of first order form. I mean, the characteristics.
Yeah, if that's your goal.
Yeah, because the idea was to compare this with what would have been obtained by Noether's theorem.
Okay.
For obvious reasons, because you want to cut out the Lagrangian root. That's what I'm saying. So, okay. So what's the?
Sorry, but I agree with Steve. For instance, this equation, if I'm correct, is the Markov Pini, the Pini equation.
Yeah.
So this is dual. So when you get the conservation law for the Markov Pini, you don't do it invariant. For instance, you should use contact symmetries, high order symmetries to get it. You can construct it from the point symmetries by.
Sure.
Multiply the conservation laws, which sometimes dependent, but in order to get the complete answer, which has to do with the integrability, and the time-dependent integrals that don't provide you any information, you should go a step further.
Yeah, but for now, what I've been concentrating on is that these multipliers, perhaps I should just mention to the audience, that these multipliers were restricted to first order derivatives, Y dashed. And let me say why I did that. When you construct first integrals via Noether symmetry, via the Lagrangian, then your multipliers will be your characteristics, which are necessarily first order derivatives. So I've tried to keep that parallel in order.
Linear.
Yeah, linear in first derivative. Yeah, it will.
We said first order. That is first order, but it's not linear.
First order, yeah, sorry. First order linear inverse derivatives. Yeah, okay. So again, your multipliers in the case of ODEs are the characteristics of the symmetry. So if your symmetry is xi dx minus eta dy, your characteristic or your multiplier then is eta minus y dash xi. Okay, of that form, where xi and eta could be functions of x and y. So if you compute that with the assumption that this is linear in y dash, then you end up with this class of these three multipliers, and correspondingly these three, each multiplier leads to a first integral. Okay, then you can find the corresponding first integral by some homotopy formula and so on. And it turns out that the homotopy integral doesn't work well, at least for me, it didn't work very well to find the corresponding first integral. So just to demonstrate as an illustrative example, how perhaps one could construct the first integral. I mean, this is a standard thing. It's straightforward, but I'll just demonstrate it for people that might not have seen this before. So you've got your multiplier, you've got the first integral, you want this to be a total derivative. That was the whole idea. Divergence, you got that. It's a single variable, a single independent variable, so it's just a total derivative of I. If you keep I to first order in derivatives, then the total derivative reduces to that. Okay, and then it's your usual thing, you're splitting and separating, etc. The kind of thing one does when you're constructing Lie symmetries by hand. You separate, etc., and solve, and you end up eventually with a first. Is this thing delayed? Yeah, or a first integral of that form. And if you check, of course, the total derivative of I1, in this case I1, this correspondingly I2, I3, ends up with your equation multiplied by that multiplier.
Just a comment, there's actually a simple way to get this.
To get what, the first integral? Yeah. Well, I put it in Maple. Maple couldn't.
How do you do it?
You don't think that's simple enough?
There's a simple line integral formula.
That line integral formula is your, is
It's
that?
not the homotopy formula.
Okay, you must please show me when you.
It's in the Bloom and Anko book.
Please show me.
I would highly recommend everyone read Bloom and Anko book as a foundation.
Please show us.
Happy to.
Yeah. Okay, so just going through, of course, this is now just throwing all the classes. It's the same procedure going through and so on. So the class of equations that generates a two-dimensional algebra would be this. Again, let me just comment on this for new students or maybe people who haven't seen or worked with second-order ODEs. I mean, if you've got a two-dimensional algebra, theoretically, you can find a solution by quadratures. Find, first of all, the commutator of x1, x2. For those of you that haven't seen it, you'll reduce it one of the symmetries, and if you did it correctly, in the correct order, the reduced equation inherits the other symmetry, and you would go on to yeah. I should comment on one more thing. When you're reducing from a second order to the first order, and if you know a symmetry of the first order, the manner in which you reduce a first order ODE can be somewhat challenging sometimes, often. Because it turns out that dealing with second and higher order ODEs is far less challenging than dealing with first order ODEs. So if any of you try to find symmetries of a first order ODE, you end up with some serious problems. Okay. As far as first order ODEs are concerned, if you would want to go the symmetry route, you hope that you can guess the symmetry by looking at the equation, or maybe that first order ODE has inherited the symmetry through some procedure, like, for example, reduction or double reduction. And then you can deal with the first order ODE via a symmetry route. And once you know you're going to deal with the first order ODE via symmetry, one of the things to do to reduce further is to map the equation, or rather the symmetry, to a translation symmetry in some transform variables, and then find your solution. It's somewhat different. For a second order ODE, if you have a symmetry, you are reducing in the following way. You take your symmetry, you find the zero and first order invariants, and then find the transform at least the change of variable, and then you end up with your first order ODE. That's not what's done for first order ODEs. Okay. And again, just going through I didn't describe it's the same procedure that I've applied here, and you end up with this first integral. Just as a point of interest, I was looking at some ideas about the relationship between symmetries and multiplies, kind of ideas that we looked at earlier and that you mentioned. What is a relationship between your Lie symmetries and your multipliers? So I've just mentioned this, by the way. I think this impacts on the kind of thing you've done in your presentation, Stephen. Okay, and then of course you've got a class of equations that may generate just one symmetry. And in this case, it's a straightforward, it's a translation in time. You could predict that symmetry, but just to guarantee that it's the only symmetry, suppose you did the calculation and you ended up with a single symmetry. And if you go through the whole multiplier route, again, keeping it first order linear in first derivative, you end up with a single multiplier and a single first integral, obviously. Well, it's not such a bad thing that you might end up with just one multiplier, because this first integral is also associated with that same symmetry. And this gives you your first order reduced ODE. It is inherited that symmetry, or in fact, you don't even have to use a symmetry. This one is, I think it's variable separable, and you can solve it. The thing is, in general, this first integral would inherit that symmetry also. And for ODEs, I mean, for you, in the classic way was to say, well, if it was a Noether symmetry and a Noether first integral, then you will have the inheritance of that symmetry to give us double reduction. Here, there's no discussion or question about Lagrangians and Noether symmetries, etc. And similarly, you have other cases. Right. So here's an example of one of the classes of those equations that nonlinear, that admits an 8-dimensional algebra of Lie symmetries, which is always just one class. It will be the SL3R. The second order ODEs will generate only one class of 8 symmetry algebra, which is the SL3R. The usual multiplier root, but let's look at the following. This is the point I'd like to make. That if you had the best Lagrangian for a linearizable equation, and this will be linearizable because you did the asymmetric, you obtained the asymmetries, you concluded it's linearizable. If you had the best Lagrangian will admit a 5-dimensional algebra of Noether symmetries, therefore correspondingly 5 first integrals. Lagrangian root. But now let's look at this as in an alternate way using the multiplier approach. Sorry, here I called it Q. So this is your multiplier. Again, let's keep it linear in first derivative and see how many multipliers we get there. And you can predict what it's going to be, because your maximal algebra that you'll be obtained by the best Lagrangian for second order ODEs will be 5. Those symmetries would have been A540, and then you get 5 first integrals. So you expect that there should be 5 first integrals if the multiplier approach covers all such symmetry, such first integrals. Oh, there was a comment. There was a comment in blue. I think I meant to say something about this one here. Is this the one with the? I wanted to look at one particular case where, even though you end up with 3 symmetries, the number of first. I'll speak about it. Please, okay, yeah. Where you are back. Okay, I'll get back to that. Okay, let's just finish this. So you expect 5 first integrals if it tallies with the old Lagrangian root. And it turns out that if you do the calculations, if you keep your multiplier first order in derivatives, you end up with 5 multipliers, right? And correspondingly, you'll find the 5 first integrals again through the same set of calculations and so on. It might look a bit horrendous, but it's manageable. mention one as yours. So yeah, the 5 cases anyways, corresponding first integrals. But of course, 2 are independent. And in this case, I think it turns out that the 2 independent ones are I1 and I2, so that the I3, I4, and I5 have those forms. But the thing to keep in mind is that you end up with 5 first integrals. And this corresponds exactly with what was established a long time ago, that the best Lagrangian for a second order ODE will admit at most 5 Noether symmetries and therefore 5 corresponding first integrals. So it's again an example of why the multiply approach is really a very good one, and it covers all such cases that you would have obtained in the past with the Lagrangian root. So this is the comment. Then the fact that via the Lagrangian root, the best number you're going to get, the best algebra will be the A540 as far as the Noether symmetries are concerned. Now I hope I can.
Because you have, they are dependent, so it does not matter, dependent or independent.
What?
I mean about you told that you have 5 invariants, right? So and then you told that only 2 of them or 3 of them are independent.
2 are independent first. The first integrals, just 2 are
It
independent.
doesn't matter, so you can get anyway. So
Yeah.
5
You will get 5. What?
independent of
You'll get 5. After you'll have to mess around with that, and you'll find that 2 of them are usually independent. Okay. Which are the independent ones is something that you're going to have to also look at. So it's a separate analysis. So these are just other cases that I wanted to mention, but I'm looking for the question. I think I overlooked that little comment in blue. Oh, this is the one. Sorry, it doesn't go back. There we are. Okay, so here's an interesting question that interesting result, that even though the differential equation admitted 2 Lie symmetries, right? The number of first integrals we end up with is 1, exactly 1. Now, why? Now, if you worked with Noether symmetries for second order ODEs in the past, you'll find that this may often happen, or may happen, that you end up with a Lagrangian. It's maybe a differential equation that ends up with a certain number of Lie symmetries. But when you go the Lagrangian route, you end up with Noether symmetries that are much less than, like in the 8-dimensional case, you end up with Noether symmetries that are less than the number of Lie symmetries. So therefore, you get that many first integrals. And it comes out here also clearly that even though you had that many Lie symmetries, the equation generated, the number of first integrals via the multiplier route is just 1. And if it's first order linear, it will be the only one. Anyway.
Again, all this is tied to your assumption that
It's first order.
we're looking at linear and y prime.
Linear and y prime, correct. Yeah. And okay, maybe I should say one more thing. The reason I kept it linear and y prime is to run the parallel between the classic Lagrangian method for determining first integrals via Noether's theorem and now. So you're right, of course, if you generalize this, you would get higher order in first derivatives and so on. Or you may get higher order in first derivatives and so on.
There's always 2 independent first integrals. They correspond to multipliers.
Yeah.
So it just means there's a multiplier of a more general form of the fashion considering.
Correct. Yeah.
Is it necessary to find them?
No.
In this case, you have
Yeah, that's the question. I mean, what in the case of second order ODEs, what are you going to do with the higher order multipliers? It's just a question.
If you want to study the gravity or super gravity, how do you want to possess a problem? I mean, sometimes you don't need to have all the conservation laws. It's not necessary. Since if you can separate the Hamilton-Jacobi position, you're fine. You can solve it. So it's not necessary to have.
Yeah.
You don't use it. Using Hamilton-Jacobi, that's it. And the Hamiltonian.
It has to do with analysis. So you're changing the whole program from just sort of algebraic viewpoint to an analysis viewpoint, and then it becomes important.
Okay, thanks. Okay, so I went, I think, much faster than I thought. I tend to speak very fast. There's some comments there about the work done before. I'll just emphasize again that a lot of the second order ODEs and so on, the work done, the classification of second order ODEs was done completely some time ago. Just one or two more comments about classification of ODEs, second order, ODEs. Faisal Mohammed and his group worked with Wafoso, attempted to classify nth order ODEs. There was success to some point, but it was quite a horrendous task. And I think eventually that task was abandoned, but they came quite close to do that. Second order ODEs, and I think they even tried third order ODEs and worked on some fourth order ODEs, I think with Astri, the same Astri that was involved in the double reduction process. And then they attempted the nth order with Wafoso. Okay, and I think that was just abandoned eventually because it was quite a task. Okay, so just some references. I want to speak a little about the references. We know this is the one you talk, this is the papers rather than the book. Faisal and Peter Leach worked a lot on this very early. I'd like to comment that we were speaking about Zurab. We're speaking about the undergraduate research kind of thing. I think this was done during his honors. And it was the start of an interesting career. I think Faisal got published like one or two papers in his honors year. So it was quite remarkable. So maybe that does support and justify looking at research at that level. Of course, we have a problem in defining what is undergraduate, but let's assume that our honors are equivalent of a fourth year undergraduate elsewhere.
It's more like, isn't Faisal highly unique among the pool of?
It is, but the point is, we never would have known if the task is not attempted, right? These are the first two papers where, well, the first one was Maria, and then a group, and some others that have taken analysis of the same. Sorry about that. Some weird latex thing that I swear I was going to fall on that. The last paper there is, I think, a lot of what you've done in that using the symmetry analysis on the multipliers as opposed to the direct first integral. Okay. Okay, and yeah, I'll stop there.
You just missed a very important reference, though,
The book,
which is not the book you're thinking of, the earlier book.
your book.
We
Yeah.
have-
I know you've got two books, right? Yeah.
It's the first book.
One was a Cheviako.
That's the second.
That's the second book.
You've missed the first book, which is just about ODE.
Okay, we'll have a look at it.
All this stuff in it.
Okay.
It's,
I always thought that was just basically all your results on PDEs that you put in the book. I mean, I haven't looked at the book, to be honest.
ODE book and PDE.
So the PDN was the one with Cheviako, correct?
There's a book called Symmetry and Integration Methods for Differential Equation.
Yeah,
Are you
that's the
referring
one.
to that one?
That's the one. Okay.
With Blumen, Enko and Blumen only. Yeah, okay. Thank you. Oh, you should get hold of that. Thank you.
Thank you, Abdul. Please, let's. We have plenty time for question and discussion, so please feel free.
I think we've had a lot of discussion anyway.
I have some comments if I can.
Yeah, sure.
Okay. Since we have time, in terms of physics, I would like to discuss with you the concept of the Lagrangian.
Sure.
So what makes for me physics different from the rest of the applied mathematics is that we have a variation principle. I mean, we want Lagrangian since we want to start from something that we variate, a principle. So in general, however, Lagrangian does not provide any physics. I mean, that's why you can have many Lagrangians for the same physical problem. However, what's unique is the Hamiltonian description. I mean, if you go in the Hamiltonian description, you have just one Hamiltonian, either if it's a conservation law or not. So if it's a if the question, if it was, if there exists a good or bad Lagrangian, it has been troubling me since I was a student, since they were trying to show us when I was a student how to construct a Lagrangian with physical interpretations. So to have some physical description, either for the single particle, for the free particle, it's very difficult to establish it physically. What we do is we consider that we have autoparallels. That means that we have a length that we want to minimize it. So what we want is the distance that the particle moves to have to apply the Hamilton's principle for the least action.
But hang on. So for the free particle equation, I thought the Lagrangian represents, I mean, this is physics, so it's beyond me.
Yes.
Represents kinetic energy.
That is
I don't know,
been
educate me.
discussed later. Initially, the Lagrangian, it is the length. It's related with the length. And then when you variate the length and you apply Hamilton's principle, which length would be the less, there will be a minimum in the action, it means that the particle we select to move in the case where it's easier for it, maybe lazy, where it's lazy. The particle is lazy. So I would like to say that in terms of physics, particles are lazy.
And you said the Hamiltonian is unique.
Yes.
So there is no one-to-one correspondence between the Lagrangian and the Hamiltonian.
The Legendre transformation, no, it's not any one-to-one correspondence.
So where does the Legendre transform?
If you go to the action principle, then it's one-to-one.
Yes, yes, but
so it's not quite.
Yes,
Because-
but you don't have. I mean, there are many terms in the Lagrangian that they eliminated when you.
Yeah, become boundary.
Yes. So yes.
So what-
boundary terms.
What is then the Legendre transformation that does?
Remove the boundary terms.
Is that what it does? Okay.
That's it. The second comment that I would like to do is something that I realized during the last years is that while we have the.
So in this case, you just thought that not all Lagrangians would have physical meaning.
Lagrangian has no physical meaning.
So the question, so in this, remember when we do this type of work, we are constructing, we are getting Lagrangians. So there has to be some expression of, sorry. There has to be an explanation of why do we have to find all these Lagrangians? What's the reason? I mean, what's the physical interpretation?
Let's not.
No, but hang on.
No,
I've been to many physics
You
talks where
answer
they
completely that
physicists
this.
assume a form of a Lagrangian based on
Yes.
Some
Energy.
physical, I mean,
It's the
Yeah.
Legendre transform of the Hamiltonian. Hamiltonian is the primary thing. that's
Yeah,
preferred.
yeah.
And there's a Legendre transform.
That does the- So
You understand that very well, you can bypass that step and you can just say, let me start with the Lagrangian. But you're really starting with the form of the Hamiltonian. And you're just using extra knowledge that you have, which allows you to reformulate it at your Lagrangian level directly. But these forms that you're talking about, they're all motivated by the form of the Hamiltonian
somewhere
Yeah.
in the background.
behind the scenes.
Yeah.
They're just not telling you explicitly.
Yeah, because you notice there was a time when someone told me about Hamilton. Why didn't you try the Hamiltonian? Of course, I shied away completely from that because my knowledge on that was zero, not even approximately zero.
But if you
Have you-
Lagrangian, you have Hamiltonian.
That is what I thought.
Yeah, and it's true.
So there is a one-to-one.
Yes, but
So that doesn't make the Hamiltonian unique.
Modulo boundary terms.
so if you apply transformation, you remove the boundary terms, and we can show it with a very simple example for the three particle. For instance, every nonlinear function of the momentum of x dot is the Lagrangian for the free particle,
Yeah.
but the Hamiltonian is just one. If you
Because I
apply
can
the
give you a list of Lagrangians for the free particle equation, and they, as far as now, let's look at as far as the symmetries are concerned, they range from the maximum 5 right down to 0.
Yes, that's.
I just find that fascinating because if the
Well,
Hamiltonian is just one.
That is the other comment that I would like to do. Conservation laws exist always. I mean, if they exist, they are there.
You don't have to find Lagrangian to say that they are
Yeah,
necessary.
yeah.
We do that. I mean, I had a very nice discussion with Sergio Hoffman,
the Mexican.
in Chile. He's Chilean. So about that, because he published some works in the 80s constructing conservation laws using not there's approach, but he used geometry in the sense that he found invariants in the phase space that they are conservation law. That's why that's a conservation law actually, the phase space. So if you have the phase space in general, a conservation law defines surfaces. So if you have many surfaces, that they connect and they are independent, you have a unique line, and that will be the unique trajectory.
Okay.
That is the concept of integrability. Now, you
should have been given this talk. I'm just joking. Yeah, I'm joking. No, it's interesting.
Sorry,
No, you're not. I'm done.
He's changed.
No, I'm
He's
joking.
changed the mathematical subject. So your mathematical subject was structural aspects.
Yes, yeah, I understand that.
Related to variational principles.
Sure.
Now he's talking about.
Sure, I'm
So
quite.
it's a different talk.
I know. It's
Okay.
interesting. I'm just joking with it.
we know well when a second order differential equation is maximum symmetric, has eight symmetries, as you mentioned well, we can write it as a three-particle.
Sure.
Okay. Take a maximum symmetric Lagrangian. The Lagrangian for the oscillator, which has 5 symmetries, is the kinetic term plus the potential.
Yeah.
X dot square plus x squared.
For the simple harmonic oscillator. Yeah.
Try the transformation that connected it, the oscillator, to the free particle. You will not get the Lagrangian for the free particle. No, because
Hang on. No. We've done one of our early works was doing exactly that, of using the notion of what is equivalent Lagrangians, of transforming the one Lagrangian to the other.
yes,
Simply because both of them generate the maximals. You couldn't do it from a 5 symmetry Lagrangian to a 3 symmetry Lagrangian, but you could do it from 5 to 5.
I forgot to mention something. Consider also that in physics you have the Hamiltonian, so you should have a specific value for the energy. So you want to have the Liouville space defined. So if you apply the transformation, you will not get the same Liouville space. And that we can see in terms of geometry. I know that you know geometry. The transformation that connects the oscillator with the free particle, it's a projective transformation. It's a transformation of the solution in the space of the solution trajectories. However, the Hamiltonian, the Liouville space, is not invariant of the projective transformation. That's why that is lost. The Hamiltonian is invariant only under isometries.
And globally, they're not the same either. I mean, you're saying the free particle is the same as harmonic
Mathematically,
oscillators.
they're equivalent.
No, only
physically.
locally, only locally.
Yes, exactly.
Globally, the trajectories are totally different.
Yes.
So I would not say they're equivalent.
They are equivalent in terms of mathematics locally. Yes.
Locally.
Yes.
Locally.
Yes.
Is the key word.
Yes. And my last two comments are related with the work of Tivari and Laxman.
Yeah.
That you presented. They have done a little different work with Claras, with Nucci. And we contact them it was my first time when I was in South Africa. I was firstly PhD, firstly postdoctoral period, and I came to work for the first time with Peter Leeds. So we were trying to find problems. We found the paper of Claras.
That one. Well, one of the related to these. Yeah.
Yes. So Clara, what she did is she took the equation that you presented. If you want to go back,
Yeah.
with Flaxman. Actually, it was she did it before.
The general one, right?
Yes, the general.
That one.
So Clara had another term here, linear in the velocity.
Yeah.
However, I'm a physicist, and in terms of physics, if I consider this part only, for instance. So for me, this is an equation of autoparallel, a geodesic equation for a particle in the one dimension. And there exists only one-dimensional space, the Clad space. So this
can be eliminated to a point transformation, to a coordinate transformation. In the coordinate transformation, I mean, we just define a variable z to be the integral E or F. I cannot write.
Oh, yeah, it's too small anyway.
I mean, there's a pen. So
A marker.
this, but I don't think that it works.
No. This is an important paper.
Yes. So if we consider the Z, the E, F, Y, the Y, we eliminate everything. And that's an easy way to say that. This term,
But that's be careful. That's when you have that linear term in y
no,
dash.
without the linear term. Either if I have the linear term, I can eliminate this. Why? I consider only this term without, I mean, just for the first time, this part. This term admits, since for me it's an autoparallel, has a Lagrangian, which is given 1/2 E 2F Y dot. So I can easily square. I can easily eliminate it like this.
Hang on, I'm not so sure about that.
I
But that's
think-
just for part of it.
Huh? Yes, for the first part.
For the first part. Oh, okay. No,
I can-
of course you can integrate that.
And I can. We contact Lakshmanan that period in 2015 and told look, we did that. We contact Clara also and we saw here that her problem reduced to the previous problem without the quadratic term. We contact Lakshmanan, he never replied. We contact Tivari was a postdoc then at the UKZN. He never replied. So we publish a comment which is like this, 3 lines.
What did Maria have to say to that?
Maria talked to Peter. I mean, probably she liked it. But
Interesting.
it was about this work. Well, see, sometimes it's better to make things more lazy. I mean, when you are lazy, it's nice. Usually by your life, I mean, when I see non-linear equations, and I try to recognize terms that I know from before. So I was able to eliminate this. And for instance, if I show you in my presentation, I had a very, very complex system, which I was able to write it gamma ijk x dot z x dot k. So these were autoparallels. These are geodesics.
Mhm.
I just work with the gammas, and I found that they are flat, so they can be eliminated before calculating symmetries, before doing anything. Sometimes it's better to work with a different.
We reached the time.
Sorry, yes, I'm sorry. So
Whew.
thank you.
Thank you. Thank you for coming.
Just a final comment.
Yeah.
It's actually simple to get the Lagrangians, so. I mean, you may not be aware of it, but you look for a variational multiplier, there's the Helmholtz condition, it reduces to a simple computation. It's not nearly as complicated as you're suggesting it is. Okay?
Unless I've just looked at the fact that they used the procedure that looked very.
They don't know
complicated.
everything.
Yeah, well, I suppose most people
But
will.
that's the problem in this kind of field is it becomes compartmentalized and there's no overview and people are repeating things and missing things and making what is a beautiful subject into something that looks overly complicated.
Well, it's via communication and so on. I mean, people are not aware of it because they're not aware of it. It's
If you don't read the literature, of course, you're not aware of things. That's all I can say on that.
but not, just a 2-minute discussion on this. You can understand why people are not going to look at everything.
No, I
That's
can't
the reality.
understand why. I have a problem with people who don't read the literature.
Maybe they're not, to attempt literature means you sort of have to know it exists for once. The second thing, which is less of a problem in these times, is maybe it's not accessible. I mean, I'll give you an example in the past. This doesn't exist now. When I started going to, for example, Pakistan, the first time, these guys, those students, and even the academics would hover around you for one thing only. Because after going to the library, they had Bloom and Gomez's book. And so I was fascinated by the fact they had this one book. But they would say, when you go back, can you please send us this paper? And at that time, it was only hard copies. And they would wait for this thing. Accessibility. Now, of course, the internet is very different. But that is the one problem in the sense that problem in this is almost completely minimized. It exists somewhere where there's maybe less internet and things like that. But there is the other problem which will never completely be solved, and that is just having knowledge of what exists out there.
Yes.
But this helps. So what I'm saying is that is why this helps. This communication.
Yes,
Yeah.
and that's why I was suggesting there should
Sure.
be more discussion sections here.
Sure.
Because we have experts here.
Sure.
We could tell everybody what the literature is.
Well, thanks for doing that. I mean, that's exactly
Well,
what
now
you
that I'm proposing, I hope it will happen.
Yeah, yeah.
It's a huge wasted opportunity.
So since we can have 1 hour after lunch, I mean, so we can do a discussion section after.
I don't know. There's something after lunch.
Yeah, so I think that, so the experts are invited to help. So there is a workshop for students. at some
Okay.
point.
Anyway.
At 3.
There is time.
So we have time to discuss if you want
For
after
example,
lunch.
I mean, that might.
I mean,
I mean, what I'm saying is this is more important for the experts
Hmm?
than for the students.
yes,
Okay.
online. Okay.
Sure.
Because if, no, let me finish, please. The reason is that, so he'll go back, and we'll supervise our students. If he doesn't know the literature, if he doesn't know all the literature, then it spreads to the next generation. And that's how we get ourselves into this situation where several generations after the original work has been done, it's been forgotten in the literature. So it's much more important that the supervisors know the literature and then they can spread it to the students. And we can have a much higher level, quicker discussion than trying to talk to students who know zero, and then I have to explain all the basic things and they're not going to get it anyways. So what I'm proposing is students can listen in, but I'm proposing a discussion amongst experts so that we try to clear up some of these misunderstandings, try to unify the subject, and try to elevate and raise the quality of mathematics that everyone in the field is doing.
Absolutely. I mean, that's just an amazing idea. Let's take it up.
Okay, we have an online question. So can we hear? You have it. They wrote it.
Just bring it to you.
Okay. Is linear type equation be a normalized differential equation so that we may do the completely group classification?
I don't understand. Is linear equation be normalized? Actually, don't understand the question, to be honest.
I don't understand.
I don't understand either. Or
Please read.
Is linear type equation be a normalized differential equation so that we may do the completely group classification?
that particular equation. Oh, okay. Now I think I'm asking.
Yeah, it's asking the equation to be normalized. The
No,
linear
no. I think
equation
he's asking the following
to be
question.
normalized so that we may
That work is done. That's exactly what this is. Yes.
Yeah.
So basically, what he's asking is, can we do the usual Lie symmetries of that particular equation, keeping the f and the g, f and g general, and then split it up as we go along and classify. But that's done. That's basically what this is about. It's done.
But I think like maybe just to mention, so in some fields, what I've noticed, what they do, like in the health sciences, they do a lot of this systematic reviews. So let's say on a particular thing, and it's very common for PhD students to study that before they go into their actual problem. But I know that it's sort of discipline specific, but that helps, like I think what Anna's saying.
Yeah.
To get an idea of where the literature is up to date, to make sure that one covers all the current. It's something we haven't been doing, but I guess
Yeah.
it's also a good way for us to
Forward.
think about.
Yeah.
Maybe,
I just thought of something,
Maybe as co-organizer, you can propose it as a result of this summer school, spring school or winter school to have that review article somewhere. I mean, so we can contribute and
Sure, we can do that, but I think it's an important for investigators.
The other thing, just one last comment, just following up from what Stephen had to say, that sometimes there's literature out there that people should know and they're not aware of or not referring to. But I think often it's a consequence of being stuck with particular set of literature. So, I mean, traditionally, we've looked at which books in symmetries? Olver and Blumen and Kume. And yeah, and Ovsyannikov, right? But what I'm saying is when people get into that mentality, that culture, the only time they move away from that is as far as the papers are concerned. But the books, they tend to stick to, oh, Peter Olver, oh, Blumen and Kume, Ovsyannikov. That's it. And when they get into that culture, believing that is gospel, I shouldn't use it, that is gospel. So when they move on from to other references, it's only at paper publication level, not at book level. So that's a good point then. You know, they assume that, oh, well, what you've done in your book is going to be very similar to what Olver did. So let's stick with the old book. And maybe that kind of culture has to change. Thank you.
Just there are also the book of Dirac. There are the books of particle physics that they actually they're doing symmetries with the same way, but they read them differently. I mean, when you have an invariant in physics, we say that it's a color, it's a spin. We give a property, but we do it exactly with the same way.
Same thing from the mathematics end. I was telling Stephen and a few people yesterday that when I just spoke a little about in the department about just talking to some students about commutators and how they work and so on, and then the discussion went on, and suddenly the differential geometer was telling me things that I found very interesting about how the Lie algebra does link in with the Lie group and so on, even though the manner in which you test these things is different. So I found it interesting. So there's other angles to that.
Yes, yes. And that's a big communication, big discussion about the curriculum. Please, let's thank.
How do we pick up the next?
So our next speaker is.
Are you next? No, it's Teboho.
Teboho.
How do I change? So what do I do? Oh. Yeah, I don't accident, you see.
Just the one that
He's gonna minimize. See that. So this one is Teboho. Which one? This one.
See, that's a big problem. There's no, let's say there's no two-way flow. There's no interaction between the different subjects.
Yeah. Especially if ODE, integrability, super integrability. Easy.
Have fun.
Geodesic equations, I mean, they're all connected.
Yes.
They're all split amongst different communities.
So our next speaker is Teboho Malachi, if I pronounce it correct. Okay. From the University of Leeds, and he will talk to us about invariance, conservation laws, and reductions for some classes of high order PDEs. So please.
Okay, good morning. So today I'll be talking about the invariance, conservation laws, and reductions of some classes of high order PDEs. We will be referring to Enko's talk, the Friday talk that he gave about the multi-reduction method. It's one of the methods that we adopted to perform the reduction. So here we have the outline, and then the background and introduction I'm going to just give because we've been talking about this since Friday. So, and then, yeah, the main objectives is to, as the topic says, investigate the applications of Lie symmetry method to discover invariant solutions of the PDEs, and also we explore the significance of conservation laws and the relationship to the study of differential equations. And as you have seen on Friday, the method presented by Enko uses the multiplier method to derive the conservation laws. And then here is just the preliminaries and definitions. which I'm going to skip. And here is the definition of the conservation law. And okay, I'm just gonna talk a little bit about the symmetry invariant of the conservation law. We assume that we have a PDE 8, which admits the time translation and the space translation symmetries amongst others. So a symmetry invariant of the conservation law is given by the multiplier condition, which was presented in the paper. And the multiplier Q tilde is defined by 10, where Rx is defined by the prolongation of X pylon to G, and then we find the vector Rx, which then we can find in. And then here I just want to remind you about the reduction of conservation laws. And then we refer back to the PBE8, and we start with the traveling wave symmetry, which has the invariant xi and u. And the invariant solution is given by u, which is equal to the big U. And xi obviously is given by x minus ct. And then you use that to reduce your ODE, I mean your PDE to an ODE. And then you use 13 to find the conservation laws that are invariant under the traveling wave symmetry. What we do a little bit different from our work is that we started with the conservation. With the conservation, in fact, we derived the multipliers and then found the corresponding conservation laws, and then tested for invariance under the symmetries that we found. Okay. And the method presented by ENCO derived the conservation laws that are invariant under the traveling wave symmetry directly without taking the first test for the invariance. Okay. And then, okay, after driving your conservation, your multipliers, you compute the corresponding conserved vectors, and then the corresponding conserved vectors can be used to determine the first integral, which uses 14. In the paper by Enko, we present an alternative formula for deriving, for determining the first integral. So in this case, we'll be using formula 14. And the example that we are going to present is for the KDV equation, which contains 3 respective sources, which is given by 15. And the coefficients, BI for I is equals to 1, 2, 3, are created by the special terms. So they are from triple, spatio-temporal, and the dual temporal. And this equation was investigated in a paper by this was Tara and other collaborators. And in that paper, they recovered the solitary wave solutions and the international conservation laws. So here we are going to show that you can use an alternative method implemented by ENCO, and then you can recover the very same solitary wave solution. Okay, so the equation 15, the KDV equation admits only the 2 points in the three, which is the time translation and the space translation. Okay, and as I mentioned that the only difference between what I'm doing here and the figure by ENCO is that ENCO derives the conservation laws that are invariant and traveling with the direction, but I start by deriving the conservation laws, and then I test them for invariance using that's symmetry invariance condition. And if that's formula that I presented, the symmetry invariance formula equal to 0, it implies that the conservation laws that correspond to that particular multiplier are associated with the solution, this case, the traveling wave solution. Okay, so we use the visual determining equation, and then we found 3 multipliers, Q1, Q2, and Q3. And then for each of the multipliers, we derive the corresponding conserved vectors using the property. And then we found that the corresponding conserved vectors are given by 1920, and then we have the conserved vector for the third multiplier. So now, okay, we call that the KDV equation that you presented admits these two symmetries, the time translation and the space translation. And their linear combination gives the traveling wave symmetry. And you can find okay, we use the traveling wave symmetry to symmetry and the multipliers that we found in the previous section to test for the symmetry invariance. As I mentioned, if this is satisfied or is equal to 0, this implies that each of the multipliers that it obtains and the corresponding conservation laws are invariant, and the traveling wave symmetry, or let me say, they are associated with the traveling wave symmetry. So now we determine the first integrals using the formula that I presented. So you notice that in the formula that you presented, there is a second term. That second term is equal to 0 for a case because the conservation laws that I presented previously don't contain, they don't explicitly contain x. So which means that when we take the partial derivative, that term will be 0. So we only focus on the first part, which is given by T1 minus 1 over C, and then T1x, which I presented in the first slide. And then first integral using the first multiplier or the first conserved vector is given by this, which is equal to K1, a constant. And the second first integral is given by psi 2. Okay, and then we will the two first integrals are functionally independent, so we will combine this first integral to obtain 24. How we combine them? For example, you can make u double prime substitution, and then you apply the second integral, and then u double prime will be eliminated, and then hence we remain with this first order nonlinear differential equation. And then here we simply are trying to find solitary wave solution. We consider the constant K1 and K2 to be 0. And then with regard to equation 25, which can be solving the correction of that and this solution, which not in the paper. And when we have shown that we do the diffraction by using the visual law, so that's the very same solution without taking into Darwin equation. Okay. And then secondly, okay, the wave profile of the solitary wave solution is given by this diagram. And then secondly, I will also be presenting an alternative method for finding and get solutions, which is a very powerful method, yet easy to to use. And that is the Kudryashov method. So in the Kudryashov method, we also start with the traveling wave symmetry. And then we can get the invariant and then the traveling wave variables. So we reduce the ODE the same way with the first method. And that equation, the PDE, our PDE will be reduced to 27 using the traveling wave variable. And then the conventional method actually starts as the power saving. And what we are trying to do is to find the coefficient in I. And M, the integer M is found by the continuous balance between the highest order derivative and the applying the homogeneous balance M is equal to 2, and by plugging M is equal to 2 on B, this will expand it. And then we get 29, and then we use 29, we will take 29 and substitute back into 27, and then make use of the equation. So it's PE has to satisfy with the equation. So we make use of this, and then we find the equation, and then and this will result in a polynomial in power of PE, and then we group polynomial in terms of the same order, and then we equate the coefficient to 0, and then we solve for the coefficient in I. The coefficient that we get is 0, and then help over A in A1, and then by that 12 over A2. And then the other part, the PE, we just simply replace the solution of the recursive equation. And yeah, we just simply replace 1 over 1 plus. The main idea here was to find the coefficient, and PE is simply given by the solution of the recursive equation, and then the wave profile is presented, and as you can see, let's wave profile and then yeah, and then okay, these are the references, and that's me. Thank you. Thank you to go for some question. Yes.
It's about M. Take 2 only, the M equal 3 equal 4 M. Question 26.
26.
M value of M equal to.
Yeah.
Yes. Give M equal to why is M equal to? Maybe M equal 3 equal 4.
We use the homogeneous balance between the highest order derivative. Control the value of M. I can say it to the same by direction of 27. I use small. Yeah. No. It depends on the equation.
Then the linear and high derivative.
Yes.
Balance.
You have
The
to,
linear and high derivative.
yeah. And then you determine the value of M.
Okay. It's about the relation P1 minus is the current relation. Right?
Now, when you were doing remember our PDE, this PDE here, when we were doing the traveling wave, when we were performing the transformation, the calculation.
Yes, I know that in a solve linear partial equation, the techniques reduce or must be current relation between coefficient of phi derivative and coefficient of nonlinear term, which is the current relation between them. Which understand. I think about the current relation related to the equation.
Let's discuss it. I think I understood. But we can discuss. So it's there's an important distinction between the two methods. So the first method, or the so the first method is much more grand. But the doing is integrating directly. The second method falls under the category of the contract. We just talk about unified expansion. Is the UEM method, and all these cousins of it, they're on that. So the first method will be in general. The second method will only be in the separate. That's an important distinction. Yes. No.
Thank you. May I see equation 25? Yeah, so this is, you mentioned about the solution is given in 2022, but in reality, it is just selector.
No, remember when I said I mentioned that this equation was presented, this solitary solution was presented by it was presented in the paper by the SWAT, not that well this solution was given by them. It was a solution for that equation. And here what I was trying to show is that using Enco's methods, we can be able to arrive at the same solution.
I didn't understand. I mean about equation 25. This is nothing else.
Yeah. So, I think we can have a break, and we continue with the final section. So, thank you a lot. Very glad to discuss it. Very glad to discuss it. Good.
So are you ready for something?
1.
Yeah. But does it look? Okay, but it is, I sent already. So.
Yes, I just want to.
Oh, you want to now?
Could I have your attention, please, before the chair will begin? I just wanted to remind you of the plans today. So at 2:30, there will be a bus going to the mathematics department on campus. And the reason for that is that at 3 o'clock, Professor Meleshko will be giving a different talk to this one. That will be from 3 to 4. And that will be in the mathematics department on campus. Then from 4 to 6, there is a possibility of several parallel sessions. One is to continue the tutorial with Reduce. Another parallel session would be a number theory session with Florian Luca and undergraduate students. So this is in connection with undergraduate research projects. And possibly a third one, if you would like to do that, would be a discussion on literature that was suggested this morning. Stefan, do you think that sounds good for you, or do you have other plans to have this literature discussion? So the literature discussion then can be at from 4 to 6, also in the math department. And then at 7 o'clock, we will have dinner in the Wine Glass restaurant in Stellenbosch. Thank you. He can join. He can join. It could be a short tutorial, and he could join after. Yeah.
Hi, everybody. So our session will start with Professor Meleshko from Institute of Computational Technology. Moshe will be speaking about exact solutions of one of kinetic models of inelastic perspective. So, principle.
Thank you. Actually, I think that my co-author, Yuri Nikolaevich Grigoriev, he is maybe on the Zoom. I hope that so he is there. And if it will be some questions, I will talk like students. If you have some questions, please ask him, not me. So I am working in School of Mathematics, and now it is changed School of Mathematics and Geoinformatics, and this is in Culinary University of Technology in Thailand. But my friend, he works in Institute of Computational Technology in the Iberian branch of Russian Academy of Science in Novosibirsk. Actually, the not title. This is my co-author. So he is. I hope that he is on the Zoom. And the topic that of this talk actually it was initiated long time ago by my friend. So Yuri Nikolaevich Grigoriev, because when I finished my graduate study, then I went to Institute of Theoretical and Applied Mechanics in Novosibirsk, and I was in lab of Yanenko. Yanenko actually he was very big guy, and so he had no time, and he had somebody who helps him. And Grigory Nikolaevich, he helped him to manage laboratory, and so we started working with him. It was the following that remember I told in previous presentation that I was lucky that I worked with Arsenikov and my advisor is Yanenko, and they are friends, and somebody told that I was a spy there. It was not spy. So then Yanenko, he worked on, in particular actually, on numerical methods. So, and also for before he had degree in differential geometry. So, and because of this, he was interested also in constructing exact solutions. And then when I talked, it was about mathematical differential constraint. So, and he told me that I have to go to the seminar of Arsenikov. And then Grigory Nikolaevich, he knew that I was involved in group analysis. So, and then he told the following, that there is a Boltzmann equation. And so for the Boltzmann equation, actually here, this is my talk. I think that I will not talk about exactly that it is solutions of one of kinetic models of inelastic processes, but I will try to introduce you in method how to construct symmetries for integral differential equations. So, and today after at 3, so I think that I will also something you will repeat. So don't be bored. But I was told that audience, it will be general audience. So then I will first start about talking about methods, so different solutions and so on. And then I will repeat maybe something from this presentation that I will talk about today. So originally, this is Boltzmann, and this is Boltzmann equation. It consists of this equation is integral differential. So here differential part, and F is distribution function. So and this is collision integral. Collision integral it is the following. So here integration with respect to sphere and with respect to three-dimensional velocity. So here this is part related with particles before collision, and this is after collision. So actually, I won't talk about this equation. So I will talk about some reduction of some reduced part of this equation. This reduction was done by Alexander Bobolev in 1975, and he used Fourier transform. So for this nonlinear equation, and I was told that his paper, when he sent to journal, it was 1 year checking. So this is correct, not correct, because original equation is nonlinear, and he used Fourier transform, and so and the question was, is it possible? So then finally he published it, and he reduced, for example, to this equation, and he found solution of this equation. So which is, of course, it is solution of the original equation. So there are only 2 solutions of the as a formula for the Boltzmann equation. It is, one is Maxwell solution, where collision integral is equal to 0, and another when collision integral is not 0. This is it was constructed by Bobolev in 1975, and later, 1 year later, it was constructed by Crook and Wu. So, but they use different ways. So. And I was suggested by Grigory. So because for this equation, it is known solution, and it was a problem. Is it possible to describe the solution by group analysis, so as invariant solutions? And we solved it, and so it was presented in 16 January 1985. Why I wrote about this? Because it was anniversary. Not, it is difficult to say anniversary because Nenkasi passed away 1 year, and it was exactly a day, 16th January of 85. And presentation was given on seminar of Arsenikov. It is general seminar for Institute of Hydrodynamics. Before explaining how to apply for such kind of equations, I will actually not remind, maybe I will just, because it will be for integral differential equation, it will be similar study. So then, for example, when you try to find symmetry, you have differential equations. Here x independent variables, u dependent variables, and p are derivatives. So then we are looking for group, one parameter group, for example. So this is transformations, and it is difficult to work with transformations because mostly they are nonlinear. So it is easy to work with something which is equivalent and with generator. So there is one-to-one correspondence between them. As generator is it is in linear space. So then we can use properties of linear algebra. So then what we are talking about transformation. So this means that we need to have some function. We have some function, original function. So this is, for example, given, and then we use this Lie group in order to transform it. How it is done? So it is substituting first part, then using inverse function theorem. So this is the key role of inverse function theorem. Inverse function theorem is local, and so then what we will have in non-local terms. So I will say later. So then it is used inverse function theorem. We find x, and then through this new variable, and substitute in second part, and we will get transformed function. And after that, for differential equation, so it is substituting equation, and it is assumed that this after transformation with new variables, so this is also is a solution of the same equation. So then this equation star, we can consider either in all variables in without bar, so this variable, or in new variables. So and then if you consider in all variables, you will get determinant equations in Lie form. So this is you just differentiate with respect to parameter, and using properties of Lie group, you will get determinant equations, which you usually be using. So, and after what was for differential equations, it was the following. After it was done such kind of equation, which is called determinant equation. After that, it was forgotten. So most papers, they write that just this part, so start from determinant equations, solve them, and you will get some symmetry. So, and if you consider new variables, so x bar, so you can do also, you can differentiate with respect to parameters, and you will get also determinant equations, but it will be a little bit different because operator before it was usual operator, so this is generator, and here it will be in Lie-Backlund form. So this canonical Lie-Backlund operator. So if you use such kind of variable, this is what is done for differential equations. So now question is how to do the same analysis for integral differential equations or equations with non-local terms. So then here the same, it can be integral differential equation, or it is stochastic or delay equation, so on. And then we assume, so this is the key word, we assume that we can do inverse, we can use inverse function theorem. So we assume that this inverse function theorem is not local. This is just assumption. After that, we do transformation, and transformation substitute. We require that solution is transformed to a solution. If for differential equation, this is the same. So, but for this one, it is not the same because of inverse function theorem. So then we can differentiate this with respect to parameter, and we will get such kind of equation. So this is similar like it was for differential equation, but it is in case that we have Lee-Backlund generator. So in generator written in Lee-Backlund form, and because here we consider this function we transform to a solution, so then this is considered on solution to this equation. So the same determinant equations like we had for differential equations. Only one thing is different, that instead of considering derivative when we use generator, it is considered in Frischer form, so in Frischer sense. So derivative for this case is considered in Frischer sense. So this is, and as I told you, we started considering this equation in the beginning. I talked about this equation, which is obtained by Bobolev from the Boltzmann equation, and then we now, because we know that we don't differentiate with respect to parameter, but we know how to get what equation will be if you differentiate with respect to parameter. So we immediately construct determinant equation. So here, determinant equation has the following form. So here, C is you can see that this is canonical path for Lee-Backlund operator. So and we can get determinant equation. So in this case, I didn't write it. Actually, it is the following. We have to substitute the determinant equations here. It is still integral differential equation. So this is answer on question. So, and it is interesting that for integral differential equations, for different types of integral differential equations, we need to use different methods how to solve it. So how to solve it means that we need to simplify it. So for differential equations, we can split, because if we have polynomial part, we split and we have many equations and we try to solve. Here, we cannot split, we have to do something. But it is very useful that to know completely about Cauchy problem. We need to know what is arbitrary and to use this arbitrariness. Actually, for differential equations, it is also used arbitrariness. When we try to split, mostly we know that if it is system in Cauchy-Kovalevskaya form, we know what is arbitrary, and then we split because of this, because of Cauchy problem, because arbitrariness is Cauchy problem. Here is the same. We need to know about initial data and about solution. So for arbitrariness of solution, this is why I'm talking about this, because when you now it is very popular fractional differential equation. But I was told that for fractional differential equations, even partial differential equations, there is no theorem of existence. We don't know what is arbitrary. So, and then because we don't know, we can construct one symmetry, another symmetry, but we cannot answer that this is complete. Oh, it's 5 minutes. I did not start with them. Oh, 15, okay. So here, for example, for this case, what we use, we know that there is Cauchy problem. So this is arbitrary function given, for example, at some moment t. And because it is arbitrary function, we can take some particular cases. And after that, we can use like for Cauchy-Kovalevskaya theorem, we know at some point, so some t, and we know how to go from this. So we know all coefficients. So, and by this case, we try to find coefficient of the following. So this is, if we know that this is initial data, so here it must be T naught. But then we have all derivatives, we can substitute in equation, and also we can substitute in equation, but we have coefficients, because coefficients, they are still, so for example, here, this coefficient, so they are still functions of not only t and x, but also of solution. So, and in order to solve this, we try to substitute particular representation of, so this is coefficient of the generator. So for example, here, they are in this form, because when we substitute an equation, this we know, and then we can take integrals. And then because this function, initial function is arbitrary, we have arbitrary number n, and we can do the limit, and we can find all these coefficients. So we use this method for such kind of equation. And finally, we found all coefficients of, oh, this one I wanted to say that the results are written in this book, so you can find them details of integration. So one more time, we have this equation. Then by this way, we can find all coefficients. And we found that admittedly algebra has the following form. It's four-dimensional Lie algebra. And after that, we can construct now solutions. So usual way, we can find invariant. We can take subalgebra. So and then for this subalgebra, we can take invariants. We can construct invariants and find solutions. So and the most important part of group analysis is to reduce number of independent variables. So we will get here the same number of independent variables will be reduced, and here some representation for solution. For example, here actually I used optimal system, of course, so because there are two ways, two approaches, and one approach is Ibrahimov told that the more constant, the better. So it is good for physicists. But for another point of view, Ovsyannikov told get rid of constants. So, for example, to use optimal system. So, and first of all, this is solution. For example, Maxwell solution. It is located in this type. So then, in this particular solution, question is that Bobolev solution. So it was BKW solution, Bobolev true, and this is formula. So, but here, using group analysis, we reduce number of variables. So then we will substitute an equation. Equation will be still integral differential equation, but number of independent variables less. And question after that, is it possible to construct some, for example, if you consider series, is it possible to cut this series? So Bobolev cut it, and he found this solution. After that, it was big boom for constructing such kind of solutions like BKW. So then BKW solution is located here. So this is for special type, one is generator. So and this is one-dimensional subalgebra. So then you don't need to consider commutator. So and BKW solution has the following form. So you can see that this is it is substitute an equation, and this part is cut. So, then we try to do something similar with equations when we have here some source term. So this for source term, it is possible to construct something similar. So to solve determinant equations similar way. But if it will be more general case, so oh, this one. So this is so maybe I will mention it a bit how it is solved, because one of very interesting properties. So this is determinant equation, and so after that, after solving this determinant equation, finally some of them, so we obtain the generator has the following form, but some constant C1, this constant Q are not known. So then for different functions, it will be different constant. So usually when you use group classification, you try to solve determinant equations with respect to some coefficient and at the same time some arbitrary function. So here coefficient we have constant and arbitrary still not solved. This is this function, and we need to solve the following equation, which is remaining equation, which is not solved yet. So, and after solving this equation, we have different representations of the algebra admitted by different functions with different functions of Q. So, and here I wanted to mention how to solve this equation, because there are several ways, and one of way, for example, in just domain equations, it is written in Ovsyannikov's book. So how to find it was some space. So this is was three-dimensional space. It was considered in order to study all possibilities. It was one-dimensional. So usual algebra, one-dimensional subspaces, two-dimensional subspaces, and three-dimensional subspaces. And then you can get all possible solutions. And for example, here it is the following four-dimensional space. So, but because we try to find some admitted generators, they compose Lie algebra. Then it's better to use properties of Lie algebra, algebraic properties. So then in order to use algebraic properties, so we start from optimal system and construct optimal system of these four operators. It will give us constant. So this constant will be given. And after that, we'll just solve such kind of equation for Q. So we will separate the problem for solving this equation at the same time for coefficients and for arbitrary functions. We have to solve at the same time. But we using algebraic approach, we separate first find constant and then using this constant find function. So okay. Next, I want to talk about, so this is, if you have here a function and not original equation. So if you have here, if you include function c, then this way that we used for solving determinant equations, it did not work. So it was complicated. And what we started thinking about, so we have we used so-called methods of preliminary group classification, which consists of the following. So we assumed that, oh, this is about full event, full mixture, that is suggested by Gazili and Ibrahimov in 95. Then it was improved. And so there are some other papers. And what we started using, we had the following. We had homogeneous equations. So for homogeneous equation, you have admitted generators already we found. So is it possible to use them for finding for function Q? Actually, yeah, it's possible. So we assume that we know this Lie algebra, and we use this Lie algebra as admitted, as equivalently group. So then using this equivalently group, we can find this function. So it will give us easier way to find the admitted Lie group in this case. So this is, as I told, for we included function C, we used preliminary classification, we found all possibilities. And so next question is that what we had, we know about BKW solution. So then question is, if we transform BKW solution by equivalence transformations, so what happens in this case? And we have to include also that kind of non-local term. So here x is actually x is velocity to the power 2 in Fourier space. And then it's possible also to use such kind of transformation. Before we had no, so now it is, we found that, not we found, it was found by some scientists from Spain for original equation. So Spiga, he published his paper related that with some particular class of right side for sources, and they found that if you use change of time, before it changed time, no, but it was not used, but if you choose change of time, so then it's possible to his solution reduced to original equations, and original equation homogeneous. So right side is here. Then you have exactly particular case of you have BKW solution. So then, and we try to use similar way. So we have such kinds of transformations. We have and try to find what will be after the transformation, what will be right side. So then it will obtain this right side of this form. And for this right side, so after that, we have some condition for this function. And so it was shown that we need to include this non-local term. So then it was done, and we obtained solutions. So we obtained the right side must be of the following form. So here, linear with respect to C. And this gives us immediately so solutions which are BKW solutions. So then it was done for one case, and then we also applied to this. So for system of equations, in particular here, system consists of two equations, and then about details I won't say. So we applied similar analysis and we found solution. So this means that when you have right side, such that the solution can be can give a formula. So like BKW solution. And at the end, I will say the result is the following. So this is usually when in this presentation, so group analysis question is, do you have physical example? So then here, my friend is constructed several physical examples of right side. And then for these cases, it's possible to have solution in exact form. So, oh, sorry, this one. The research was supported by Russian Science Foundation grant. So, and thank you very much.
Thank you so much, Professor Minister. Question, please.
Yeah, very clear as usual.
Yeah, as usual. Thank you so much, Prof. Thank you.
Thank you.
Yeah, I will make a speaker is Dr. Alexander Jessica from Big University. She will be talking about symmetries and communication laws of boundary value projects.
Morning, everyone. Sorry, I'm still trying to find the page down button on this. The arrow. Okay. So we start off as usual, slightly theoretically, we're talking about the paper differential equation. Actually, in the example, it's going to be a second order differential equation. Not to spoil the surprise, but it's going to be everybody's favorite, the Hughes equation. But in principle, the equation depends on independent variables, some dependent variables, and we have some symmetry generators. Such that we transform the equation, it vanishes on solutions of the equation. But if you want to insist on a boundary condition for this problem, not all of the symmetry generators that we found are going to be compatible with that boundary value. It was thought at one point that, well, before I say that, our Hughes equation, I'm going to take a very basic form where all constants are equal to 1. And we have, the collection of symmetry generators. The one that's going to be a big interest to us is this last one. This arbitrary solution of the Hughes equation that modifies the dividing new term. But we add an initial condition. I pick this one that is equal to 0. Our function should be equal to e to the x minus 1 or 0, whichever one is bigger. Actually, this means the x minus 1 when x is positive and 0 when x is negative. It's the same thing. Which symmetry generators can we keep? That's the requirement is that the boundary condition should be non-invariant, but it's sufficient, but it's not necessary. Actually, all you need is that at the boundary value, everything satisfies the invariant surface condition. So the invariant surface condition, you get one for each independent variable, and it's well known in the literature. That's what it looks like, and it has to hold in particular at whatever boundary we are talking about. If necessary, we will use the equation in our example, the East equation, to make substitutions if we need to. And there's a very nice paper about it by Joanna Ford from Australia. I think you're the first one to notice that this is this is an easier yes or no condition. So for the heat equation, with the boundary condition that we talked about earlier, our general symmetry that will be allowed with the boundary condition will be of that form. It will be a linear combination of the ones that I listed a couple of slides ago. And the non-invariant, the invariant surface condition means that this equation has to be satisfied at all points, including at the boundary. The boundary just equal to 0. F of x here is is this guy. And so we just make that substitution, and also at the boundary, it's hard to take derivatives with respect to c because at the boundary t is equal to 0, so we can make the substitution. It just comes from the heat equation itself. The invariant surface condition becomes fairly simple, and if we take a linear combination of the previous of the symmetries count, the invariant surface condition ends up giving you that this is your most general symmetry generator that will allow that boundary condition. Now, you need to figure out depending on which function psi. Maybe if I take back a little bit, just to remind you, psi is the coefficient of things like mu, which is up until now the arbitrary solution of the heat equation. We have a boundary condition on that. If you have a look at these constants, C1, C2, C6, if you pick them carefully, not that carefully, you see how to do it, you can actually find that this boundary condition can be the same as the original boundary condition from my original problem. That makes me think that there must be some sort of recursive method for finding the function psi using that recursive property that we see. But I haven't figured out how, and perhaps somebody more knowledgeable than I might be able to suggest a foothold into that. But in my ignorance, what I did was I gave myself a nice and easy symmetry by picking a couple of nice values for the C's. And then you can just take a fundamental solution of the heat equation, which Professor Anker mentioned, one of the solutions we found using conservation law. And you take a convolution of this function with this boundary condition, and you get a nice, the integration is not so bad, and we have a form for our previously arbitrary function psi. This is what it has to look like now. This is not the solution of the heat equation. All we've done so far is find a symmetry that will admit the boundary condition. So now, how do we find the solution for the original boundary condition, boundary value problem? We set up the Lagrange-Charpy equations as usual. We solve them, and after a couple of steps, we get a nice-ish looking solution. Again, the integration is not too hard. A question that nobody has been good enough to interrupt me with yet is, why did I choose the boundary condition that I did choose? There are a couple of reasons for it. One is that it's not too difficult to work with, and I like to be kind to myself. The other reason is that the function is exponential and then flat. So it's exponential for positive values of x, flat for negative values of x. And at that corner, it's not smooth, but that is not a problem. So one of the things we're demonstrating here is that the boundary, the initial condition or the boundary condition does not have to be smooth everywhere. In principle, if I go back a little bit, this function f, it could be quite badly behaved, and we could find the function psi by taking a convolution with the fundamental solution of the heat equation. In principle, you can do it for almost any function f. It doesn't have to be very well behaved at all. So that means that there's actually quite a wide class of boundary conditions that you can handle this way. But the other reason why I chose that boundary factor is because it happens to be a boundary value that comes from the Black-Scholes equation. So there's a sequence of the Black-Scholes equation for a European call option. This is the Black-Scholes equation. I'm not going to say too much about it. R is the risk-free interest rate. Sigma squared is the volatility of the market. E is the price of the stock option, and S is the value of the underlying asset. For those of you who know about financial world, you can probably tell me more about it than I can tell you. But and then the boundary value for the Black-Scholes equation, it's actually a terminal condition. The value of the option is the difference between the value of the underlying assets and the option price, if that difference is positive. There's a fairly well-known sequence of transformation, which I'm listing here. I won't take you through all the details because I've actually taken the engineers in my data, and they, even though they need to see the details, they hate watching me do the details. They simply fall asleep. And if you want to know the details, you're welcome to come and talk to me about it afterwards. That sequence of transformations transforms that Scholes equation with that terminal condition into the heat equation with the initial condition we just discussed. So you can back transform, and you have a nice solution to the Black-Scholes equation for the European core option. This transformation, by the way, you can also derive it using symmetry methods. And in the references, I've got a paper where it's done. But also I will say that the sequence of transformation is very widely known. I actually got it off somebody's blog without reference. But there's lots of ways we can do it. And here's a nice picture of what the solution actually looks like. So it looks almost flat at the back, but you do have that point where the terminal, this is now the terminal condition for the Black-Scholes equation, and you have again that point where the boundary values are not smooth. We've got the corner and the derivative does not exist there, but we have still managed to solve it. I also wanted to talk about conservation laws. It's my embarrassment I haven't actually found any, and it's not because I don't think they exist. I think it's just because I'm too slow. So that's something I still want to work on. There are a lot of questions that I still have about all of this. A big one is how many more boundary conditions can we add before symmetry method will let us down. Another one is in this particular example, I had a little bit of luck, which is that in the symmetries of the heat equation, there was that one, the infinite dimensional symmetry involving the arbitrary constant of the arbitrary solution of the heat equation, which gives the symmetry a lot of power. It can handle a lot of things that we inherited. If the equation that you are dealing with is not so rich in symmetry, what can you do? I don't know yet. Maybe if you can transform it to the heat equation or something similar and manufacture symmetries, maybe you can get away with it. The Black-Scholes equation, by the way, has also, if you work out the symmetries for the Black-Scholes equation, you'll see that it also is rich in symmetries like that. It also, one of its symmetries depends on an arbitrary solution of the heat equation. Other questions in terms of applications, the Black-Scholes equation is known not to be actually very realistic. It's so can be generalized to what happens if the interest rates is time dependent. What happens if the market volatility is time dependent? What happens if you add on extra terms? Transforming it to the heat equation by the same series of steps under those assumptions, it can still be done. Solving it made me scratch my head a little bit, and I haven't figured out how to do that yet. But that's something that I'm still looking at. And other questions that a partial answer to my previous question about if your equation is not so rich in symmetry, what can we do? I'm going to be finished in the group. I'm almost done. But if your equation is not so rich in symmetry and you have a nasty looking boundary condition, perhaps you can start looking at approximate boundary conditions that will be admitted by the symmetry. So that's an avenue for exploration, but I haven't been doing that. So the only other thing is to throw up a couple of references. The first reference is a paper by Joanna Board, where she first suggests that the invariant surface condition is a better condition for deciding whether a boundary value problem will be admitted by a group of symmetries. The middle one is a small tube of my own trumpet. I published some of these results. The last one is a paper where, if you want to see how you have use symmetry methods to transform Black-Scholes into the heat equation, that's where you can find it. So a short list of references. I think the big ones have all been mentioned many times already. And thank you for your attention.
Thank you so much, Dr. Alison. Any questions? We have more time. Yes, sure.
13, how this Black-Scholes equation is reduced to the heat equation. It was much earlier.
I'm sure it was. because the transformation of one equation to the other, I think, is been well covered.
To transform the Black-Scholes equation to transform to the heap equation. So
Yeah.
homogeneous.
So I was a little bit lazy with my reference because I didn't go back to the first one where it was done. I found the reference where it was done, and
So your question about conservation laws, they're all known. So if you're interested, I can just tell you what they are.
yes, please.
All. The second question, how do you handle general boundary conditions? Well, the general answer is going to be once you know the conditions in the equation, you can then just write down the general form for a suitable boundary condition for which this method will work.
Yeah.
It's not hard to do. Right, so that's, you have to take on for it's compatible, but that's because you have the symmetry. But if you only have a finite dimension, it's just rapid.
Yeah. Yeah, so then there's a much smaller class of boundary.
No, it's not. I think they work it all out. But I guess the big comment I have kind of dictates everything. I don't know, maybe I can think about it.
No, I think that I have heaps of ignorance, and I think it is. I mean, people are interested in boundary value.
So the big comment is, well, look, the only reason we have the integration of the symmetry is because we can map the problem into the if we're only in equation, we know how to solve it, the convolution.
Yeah.
So you don't need symmetry methods at all.
No, you don't need them.
You take the original equation of the black pairs with your condition, plug it into the convolution formula, evaluate the integral, and done.
It's true.
So the question is, from that point of view, it's solely the grading, but the way the reinstate it, you just say somehow that something in the symmetry equation, but I'm not sure if that's good.
So that's why I made that comment about if you pick your constants in the general symmetry correctly, the boundary value for the arbitrary function is the same as the original boundary value problem. And if there's a way of kind of bootstrapping that and using that recurrence, it becomes a much nicer method. So yeah, the fact that I had to step kind of outside the symmetry box and use a convolution, it bothers me, but that is where I had to. Right, but if I was completely focused on the solution, then that would be a much quicker way of solving the problem. But at least for now, I know that there are some symmetries associated with this. It's true. So if you can solve one, you can solve the other one. But
Sorry, this is it's not a question specifically for your talk, but maybe more to Stefan and others in the research field as well. So differential equations are very important things for your life, and I would imagine that many people in their working environments end up having to solve certain equations. And it seems like from the comments, especially of Stefan's comments, that there doesn't seem to be an online website for that catalogs all the techniques, existing techniques, and the new ones that could arise. It shouldn't be difficult to get funding for such a thing because of the impact it could have. So that would be a kind of suggestion to create such a website, or if it already exists, it would be good to know. I will chat with Professor Moy and we'll come up with a plan.
It has a nice 3-volume books. So he collected many results, and I remember even Peter Olbert, he told that it was very good. That it was constructed. It was published 3-volume handbook of Lie group analysis, but it is old. So this is good idea that now, because it was 96 maybe last one. So this passed already many years. So it will be good to have new by internet.
So just to give an example of two online resources which have been very effective in two different areas of mathematics. So one is the online encyclopedia of integer sequences, which catalogs sequences in number theory and combinatorics. And the other is, that was actually started by one person. Originally, it was a handbook. And the other is the N category cafe. This is a place where category theories, especially higher dimensional category theories, write up almost all of category theory. I use both of them quite often for not so. The second one is not so good for references, but the first one is very good for both references and knowing which sequences are known. So such things definitely exist and they do work.
All right, our next speaker is Dr. Kathleen from University of Victoria. He will be presenting a similarity solution for a three-dimensional Newton structure in a cylinder rock.
Good afternoon, everyone, and thank you, the speakers. As the speaker said, my name is Marcel and I'm from University of Victoria. My talk is entitled "A Similarity Solution for a Pre-Existing Fluid-Driven Fracture in a Permeable Rock." So this is just an overview of the sections that I'll cover. I'll just briefly give an introduction and background, and then look at the mathematical models and similarity solution, and then I'll give an outline of the numerical scheme and conclusion. Sorry. So first, we can just discuss what is hydraulic fracturing. Prof. Mason yesterday has covered that in length, but we'll just discuss it again. So hydraulic fracturing is a process that is used in the petroleum and mining industry to open up fractures. We're interested in opening up these fractures in order to be able to access mineral resources and gas that is trapped underneath. One of the techniques that is used is hydraulic fracturing, and is said to be a advanced production method or an unconventional gas extraction technique. So it is said so because in some cases, conventional gas is such that gas is concentrated in a specific gas reservoir, and all you need to do is to drill, have a vertical drill and just have a well and extract that gas. However, in some cases, you find that your gas is dispersed across the rock, and in that case, you need to open fractures into the rock to be able to access the gas that is trapped within the pores of the rock. So the idea here is that you pump a viscous fluid into a rock fracture at ultra high pressure in order to propagate it. So this method was introduced in the 1950s, and it has become, a core technology for reservoir stimulation, drilling cuttings, and geothermal energy generation, which Prof. Mason discussed at length yesterday. So these fractures, as I've said, they can be man-made or they can just occur naturally. Man-made fractures will be these hydraulic fractures, while the naturally occurring fractures will be kilometers long volcanic dikes driven by magma. So during this process of hydraulic fracturing, it has been reported that
in a case where the rock is permeable, there will be some loss of fluid into the surrounding rock. And many models have been developed to try to model this fluid leak-off. Amongst the common models being the KTAS model, and there's also Darcy and Isbash model. These models are not without limitation, of course. For example, the KTAS model is only limited for a small time range, and the Darcy also is limited for, it's just a good approximation for a limited velocity range. Farrier and Mason, when they considered the problem of a fluid-driven fracture in PKN theory, they assumed a linear relationship between the leak-off velocity and the fracture half width, right? And they also, in their work, making a suggestion that one can relate the leak-off velocity to the gradient of the fluid rock interface. However, in all of this and their results, they did not actually give a justification and motivation as to why one can do that. And part of this work was to do that justification. And we present a leak-off model in which case the leak-off velocity is proportional to the fracture half width and the gradient of the fluid rock interface. Now, the rock, the schematic here is just our two-dimensional hydraulic fracture, and we're assuming that our fracture extends in the positive x direction and in the negative x direction. And our QL here, it will be the fluid that has, the flow rate of the fluid that has leaked off. And between here, the x-axis, and here is our half width of the fracture, and here is our a fracture entry. So we are assuming that the source will be coming from here and go in that direction and go in that direction. And yeah, so we going to assume symmetry about the x-axis and the z-axis, and the as a result of assuming symmetry, we are going to only consider this region of the fracture, and also across the z-axis, it just allows us to be able to consider this side of the fracture, which is just our first quadrant. So in terms of assumptions, we just make the standard assumption. We assume that our fluid flow in the fracture is laminar, and the fracturing fluid is also a viscous, incompressible Newtonian fluid. We assume lubrication theory, and of course, our medium, we assume also that is permeable. So there will be some part of the fracturing fluid that will leak off into the surrounding rock mass. And as I've said, our fracture will propagate in the positive and x direction, and our length will be given by LT and half width HT of x. And this is the condition where we assume symmetry about the x and z axis. And as a result, we are just going to focus on the region where x is between 0 and L of t. And we assume that our fluid flow inside the fracture obeys or satisfies the Navier-Stokes equation and the conservation of mass equation for an incompressible Newtonian fluid. And we are able to obtain this dimensionless lubrication equation. These equations are standard, and the associated boundary conditions are given by equation 3.4 and 3.5. Equation 3.4 is the no-slip condition, while 3.5 is our leak-off condition. So now we want to derive the nonlinear diffusion equation that relates our half width of the fracture, the pressure, and the leak-off velocity. And to do that, we just integrate the equation in 3.1, and subject to 3.4, we obtain 3.6. And from 3.2, we can just see that our pressure does not vary across the fracture. And the important equation here to note is equation 3.8, which is our nonlinear diffusion equation relating the half width of the fracture and pressure and leak-off velocity. Now, for us to be able to solve this equation, we need to specify a Lickhoff model so that the problem only just needs to be solved for the pressure and the half width of the fracture. So in their work, Robel and Meshuris presented the idea or argued that there are various external conditions that affect the modeling of a Lickhoff function, some of which include the geometry of the interface, porosity, fluid saturation, and the other factors that are stated there. And they indicate that with these conditions, the model becomes, or rather the problem becomes greatly complicated. However, they did also suggest that it is often just necessary to just specify your Lickhoff function in terms of the measurable quantities of the hydraulic fracture process, which in that case, it is just our fracture half width, net pressure, and the adjoining rock properties. And as a result, our function VLL is just a function of T, X, and H and P. H there is our fracture half width, and P is our pressure. And upon doing more investigation, we found this literature that specify that, one can also include the viscosity and permeability, which is, of course, something we expect, particularly because the viscosity and permeability also present some, they are there in the Darcy model. And with a dimensionality analysis, we're able to obtain the relationship given in 3.10. And our Lickhoff model in this work was based on this result. Now, we have to now close the model. We do that by giving a relationship between our net fluid pressure and the half width of the fracture. And in this case, we just use the KGD elasticity model given by equation 3.11. And yeah, again, Prof. Mason discussed this relationship yesterday. And what is important also for us to note is that the pressure given on the left-hand side is our net pressure, which is just the difference between the pressure inside the fracture and the normal stress at infinity. And we also specify our stress intensity factor. More than what Prof. Mason have said, that it only makes physical sense for one to define the stretch state outside of the fracture, and it also helps with similarity solution. Moreover, over those two reasons, we also need this condition for setting up our numerical scheme. So both the equation in 3.11 and 3.2 in dimensionless form are given by 3.13 and 3.14. And the gamma here then becomes our dimensionless stress intensity factor. Well, we state, since our fracture is pre-existing, we state the normalization condition, which just tells us that the fracture, the half width of the fracture at the fracture entry is 1, and the length is also 1. And 3.16 states that our fracture vanishes at the fracture entry. And we also specify that our fracture, we assume that is smooth and that is symmetric about the z-axis. As a result, we have this condition that our slope is 0. I must also state that this condition also comes out if one invert 3.13 and evaluate the gradient at the gradient of the fracture half width at 0. This condition also you can be obtained there. Now, 3.18, we specify the final condition, which is our mass balance law, just telling us that the rate of change of the volume of the fracture is the difference between what is coming in and what is going out. And 3.20 is our flow rate of the fluid that is leaked off. In this equation, in this slide, what is important for us to note is the flow rate at the fracture entry given by equation 3.23. And after we substitute the values we got into the specified mass balance law and performing dimensionality, obtaining the balance law in dimensionless form, we get equation 3.25. So for the remainder of the presentation, I'm going to just be removing or rather suppressing the overhead bars with the assumption that it's known that they are dimensionless. So now we look for the similarity solution of the form given in equation 4.1, where we just use separation of variables. And if we substitute that equation, those equations into our model from the previous slides, we obtain this system of which is a integral ordinary differential equation that needs to be solved for f of psi, g of psi, and p of psi, and the conditions are 4.4 and 4.5. Now, for us, well, once we are able to solve that, of course, our functions take the form specified in 4.7 to 4.10. And in similarity functions, our mass balance law is given by 4.11. Now, for us to be able to solve that system that we specified, we need to specify the function for the similarity function G, or state a relation between G and f of psi. And in this work, we specified the relation between G of psi and f of psi. And as a result, our pair of equations was now left to just solve for f of psi and p of psi, subject to the boundary conditions. And of course, we still had the constant C2 that was still showing, and C3. And C2, we used the mass balance law to obtain it, and C3, we absorbed it in the Likov parameters. And we assumed this form given by equation 4.12, in that our similarity function G is proportional to similarity function f of psi and its gradient. And beta 1 and beta 2 are our Likov parameters. And with that assumption, we're able to obtain equation 4.13, which tells us that our Likov velocity is proportional to it's a linear combination of the fracture half width and the gradient of the fluid rock interface. Now, with this model given in equation 4.3, we now have three possible cases of Likov. The first being the case where beta 1 is greater than 0 and beta 2 is 0. And in that case, our Likov velocity will be proportional to the fracture half width. And the second case will be beta 1 being 0 and beta 2 greater than 0. And we have the Likov velocity being proportional to the gradient of the fluid rock interface. And the last case is the general case that I've already stated. And of course, another case, which is not Likov, is when both are 0. It means that our medium is impermeable. Now, what I wanted to highlight here is that we have our mass balance law given by equation 17. And it's also important that from the diffusion equation, if one integrates that equation in 4.13 from psi to 1, we can still obtain the mass balance law if we evaluate that equation at psi equals to 0. So outside of the mass balance, rather equation that we have defined, one can also obtain it from the diffusion equation. Now, before we just chose random values of beta 1 and beta 2, but after some time we observed that these numbers, for some numbers of beta 1 and beta 2, the solution was not working. And then we had to just think about how we can find a restriction for these values, or how to know which values to choose and which values not to choose. And from equation 4.19, we just assuming that the area under our fracture is greater than a half and but still less than 1, based on the fact that our fracture at the fracture entry initially is 1 and at the fracture end is 0, and that it decreases monotonically. And also, we know that for our fracture to grow, C2 must be greater than 0, which from 4.18 just gives us this condition given by equation 4.21. So as a result, after some algebraic manipulations, we were able to obtain equation 4.22, which just tells us that for a specified value of Q0, there is a restriction on the choices of beta 1 and beta D2. Now, we have an understanding of how our fracture behaves at the fracture entry and its slope. However, at the fracture end, we do not have much information other than our fracture vanishes there. And with the assumption that this fracture decreases monotonically, we want to understand the behavior of the fracture towards the end so that we can set up our numerical scheme to accommodate any singularities at the fracture end. And for the case in which our stress intensity factor was 0, we obtained the following asymptotic solutions. And for when it was greater than 0, we obtained the following asymptotic solution. So it is important to note that for equation 4.26, if one takes the derivative there and try to evaluate that term, or that term near psi equals to 1, it tends to infinity, minus infinity. And this is the information that helped us solve this problem, or rather set up a numerical scheme that can handle the singularity towards the fracture end. So with this knowledge, our aim became to extract the tip behavior, and then we represented the remaining part of the similarity function as a linear spline. And for us to do this, we divided the domain into the domain 0 to 1 into n equally spaced subintervals, and we represented our function f of psi in each subdomain, rather in each interval as the equation given by 5.1, and our piecewise linear function is given by 5.2. And then we move to discretize our nonlinear diffusion equation, where we approximated the first and second derivative of the pressure using the central difference at midpoint in a uniform grid. And what we observed was that there are two problems that we encountered. Was that when I was equals to 1 and when I was equals to n minus 1, the nodes, we will have those nodes which we evaluate psi at minus half and n plus half, which lies outside of our domain. So the first part, we handled it using symmetry to say that p at minus 1/2 is equals to p at half. And the other domain where we are evaluating p at n plus 1/2, we use the stress intensity factor because that's the pressure just outside the fracture interface. Now, if we substitute our function into our Cauchy principal value integral, we obtain this form of the pressure. And it must be noted that this P is evaluated at the mid-grid points in order to try to avoid the singularity. However, for each value of I, there will still exist an interval into which the singularity still exists. What was interesting was to note that the built-in MATLAB function was able to handle this singularity. Even though it complained, it was still able to handle it, but the SciPy in Python was not able to handle the singularity up until you use the method of subtracting the singularity, and then only then can it work. And of course, if you do that, we obtain this expression. And from this expression, the singularity that remains is the endpoint singularity, which the MATLAB quad GK can handle. And the remaining integral equations that are Cauchy principal can just be evaluated as shown in equation 5.7. And now the problem was just to solve a system of non-algebraic equations, non-linear algebraic equations, and we just need to solve for the coefficients IA and BI, and there are 2n of those. So from that first discretized non-diffusion equation, we're able to get n-1 equations, and using the condition that states that two splines are common at their interior points, we're able to get an additional n-1 equation, making them 2n-2 equations, and we use the boundary conditions to eliminate two additional we eliminated two unknowns, and as a result, our system we can be solved since it's 2n-2 nonlinear equations in 2n-2 unknowns. And yeah, and now all we needed now was to just specify the value of Q naught and gamma. And once we have done that, we iterated based on the bisection method with varying values of C2 up until our mass balance law was satisfied. And from the solution, we obtained our value of C2, and this is the results that we obtained. And of course, these results were expected, as for the case in which the Likov parameter was high, the extent of growth was the least, and even the shape of the Likov velocity for when the fracture, rather when the Likov velocity is proportional to the fracture half width, is something that we had expected. And this is the result when the Likov velocity was proportional to the gradient of the fluid rock interface, and we can see this behavior there also is something that was expected. And this was result for the general case. What was interesting to see was that for the values, where beta was 0, 0, 1, and beta 2 was 0, 0, 1, and which other case? Yeah. No, actually, this case and this case were the case which our Likov extent of fracture half width were the same. Yeah, it was I still haven't figured out those results, why that was the case, but that was what the mathematics gave us. So now the conclusion here is that we just investigated a two-dimensional fracture, which was pre-existing, and it was evolving in a permeable medium, and we gave a Likov model, in which case it was a linear combination of the fracture half width and its gradient. And also we gave a justification why one can do that. And this normalization condition also we're able to obtain it. We have not seen it in literature before, because most problem investigate problems that are evolving from point source, meaning that they are not pre-existing. And finally, the result is just something that we have expected. And yeah, these are the references that I've used, and thank you for your time.
Thank you so much, Dr. Shabley. Questions? No?
It was clear.
Thank you so much.
Yeah.
Yeah. Thank you so much. Thank you.
Okay. Thank you.
Oh, sorry.
It's you.
Yes, the last one.
Want to start with tomorrow?
Oh,
Yeah, the last one. So you have like.
Does anyone need transport to go to, I think at 3, sorry.
The maths department.
Yes, to the maths department. Okay, no one needs transport. 1, 2, 3. Okay,
What
3.
time is that? Is that 3 o'clock?
Yes,
3.
we're gonna fetch you at
After
2:30.
lunch.
After lunch, 2:30. It's just 3.
We know the directions of where it is. Forget what.
I don't even know where it is. He's gone already. They have a picnic.
That's what the maths department.
Yes. But I'll be driving behind them, so.
You will see the small department. Yeah. Get your correct name because I want them to adjourn the chair.
oh, I see. Salama. My last name is Umar.
And then you next is this.
Yeah, excuse for the last 15 minutes because I need to go to mosque.
No problem. Everybody is going to the mosque together with so we take it next shot out and then you go to lunch afterwards.
Yes, but I do ask someone to come to
No
the
problem.
Yes.
Studies.
Okay.
Yeah.
We're able to continue this session. The chairperson will be able to continue because we will just stay for the first 15 minutes and then I will go.
I can do it.
Yeah, I'll just not now.
I can finish it.
Okay. Yeah, because I'm leaving. All right. Unfortunately, this conference comes to end, and this will be our last presentation, unfortunately. Yeah, so our speaker will be Dr. Robert Bogadi from Durban University of Technology, and he will be talking about compactification of gravitational field equations in higher dimensions. So please start.
All right. Thank you. Thank you also to Prof. Sibu for hosting me here. I must say, I'm pretty new to differential equations, but I do use them. And that's why I've come here to learn a bit more about the Lie symmetries. And that's because I'm working with Professor Megandran Govender. Originally, he was from physics, but also in applied maths at Hart College, UKZN. And now he is working in mathematics department at Durban University of Technology. And we draw our strength from Prof. Moya too, who's encouraged us to do our work. And we will need now expertise, I think, in Lie symmetries, as you will see, in the systems that we study. So we basically work in the field of general relativity, and I just put in very few basic references. Obviously, the foundation of general relativity, I think it's no surprise to anyone, from Albert Einstein. So we can see the theory of relativity is well over 100 years old. And in that time, things have progressed, I must say.
Einstein was unhappy, obviously, with his equations, because when you look at it from the cosmological point of view, he assumed he wanted the universe to sort of be a static, not to contract or to expand. And as time progressed, we have now discovered that the universe is expanding, not just expanding, it's in fact accelerating. And this is something that is problematic to us in general relativity. Of course, Einstein, he introduced something called a cosmological constant, and then he withdrew it, and then it got put back again. And since this cosmological constant, it's kind of a small correction in a way to general relativity, but people have looked at this more carefully, and they've thought, well, maybe there are some modifications to general relativity, some modified gravity theories. And part of these modified gravity theories have now become part of what's called gravity in higher dimensions. And it's interesting that I think it was in 1971, there was a form of gravity called the Lovelock gravity, which was actually approached through the Lagrangian points aspect, where you take your Lagrangian density, you find the action you minimize the action, and through that you can actually then obtain the equations for general relativity. And from that, basically, one can then extend into these higher dimensions. And I'll come back to some other references. There's also an important one, Dadich, progressing with the years. He's also looked at the gravity in higher dimensions. And this is also, we used the work of Bar a little bit. That kind of sparked my interest in higher dimensions, as you will see in the forthcoming slides. Okay, so I just kept this really, really simple. I'm not going to be solving any complicated equations. I'm just pointing out the equations that we're dealing with. These are the Einstein field equations. And at first glance, it could look innocent. And the whole idea is to basically solve this object. And this is called the metric tensor. And basically, the left-hand side of the field equations describes the geometry of the space-time. And the right-hand side then describes the matter-energy content. And so Einstein's insight was to basically find this equation, which basically says that the matter content influences the geometry of the space. And then that changes the geometry. The geometry then tells the matter how to move, in a sense. And this is the cosmological constant, which actually was a lot of controversy through the past century or so of general relativity. In my case, I don't really look much at cosmology. I'm looking more at compact objects, and so we usually ignore this. But when you look at cosmological solutions, you cannot ignore that. But it is a small value, but people look at that. It's not negligible. Okay. And that's basically sparked now the interest in things like the dark matter and dark energy, which people now don't know how to measure. It's not measurable. Where does it exist? We don't know. Is it in a higher dimension? These are all questions to be asked. Okay, so looking a bit more carefully at the left-hand side, this is actually known as the Einstein tensor. And the Einstein tensor then is composed of something called the Ricci tensor. And that is a contraction of the Riemann tensor. And these objects all measure the curvature of the space. And then we have a big R as a curvature scalar, which measures a sort of average curvature. And so inside here, we've got the metric tensor, and that's the object that we're trying to solve for. And as we expand these tensors, it actually starts to get quite complicated, and we end up with these so-called connection coefficients. And with inside these connection coefficients, these actually are not tensors, but they've got an important job to do in which they connect the directions of, depending on how you travel inside the space-time, how the directions affect each other. And inside these connection coefficients, also they're called the Christoffel symbols. You've got, again, these the metric tensor. So it actually does get quite complicated quite quickly. So, sorry, this is a little bit small. What happened to my slide there? It's almost unreadable. I don't know what happened to that. I don't think it's too important right now to interrupt the flow, but I'll get back to this. But so we're trying to solve for the metric tensor so that we can describe what is called the line element. So the line element then allows us to progress in the space. So basically, if you have an extremely massive object, then as you get closer to that object, the metric tensor will basically tell you how to navigate in that way. And let's move on to the next one. So basically, in my line of work, we try to keep things as simple as we can because things get complicated quickly. So we try to firstly look at things like spherical symmetric line elements. And so the A, the B, and the C, those are the metric functions. And even we can make it simpler. We can just look at something like what's called a shear-free metric. So we only solve for these two objects, A and B, and these are both functions of spatially and temporal coordinates. And when one runs this through the Einstein field equations, you can generate the fields. So the rho, the PR, and the PT, that comes from the energy momentum tensor, and that's basically the matter field. So the rho is the energy density, PR and PT, those are pressures, and the Q is a heat flux. And so inside of all of that, you've got these A and the B, and also we kind of talk about A and B as gravitational potentials. I know it's a more classical way of seeing it. Instead of metric potentials, we interchangeably use the name, say, gravitational potentials for that. So what do we do with this now, once we've got that? So you see, we've got A and B inside here. We've got derivatives with respect to R, radial coordinate, and we've got the dots, double dots. So it's derivatives in time. And then we can play some games with this. We can say, well, maybe we have an isotropic system. Perhaps we make PR and PT equivalents. Okay, because the R is a radial pressure and the T is a tangential pressure. We can equate them and see, can we get solutions? And we can also look at things like a boundary condition, which the scientists have worked on, and they've discovered that if you have a system which is non-static, then the boundary, say you have a system in which the matter content is collapsing, then you will have, say, a radiation flux. And so then the radial pressure is actually equated to the heat flux at the boundary surface. And so you can imagine now when you take this PR and you equate it with the Q, you could get something a little bit nasty to work with. And then this becomes, this needs to be handled in a way, say you could try to use your Lie symmetries. And there's some smart people in UKZN, Prof. Maharaj, they go and try and find exact solutions which satisfy such a boundary condition. And one can also look at static models. So if you maybe ignore the time dependence, you look at a model in which the time does not change anything, say a neutron star, which is not collapsing, then you could maybe look at static potentials. And then in that case, there is actually no heat flux. So your boundary condition is a lot simpler. So one can equate this to 0 and again look for solutions. And again, maybe one can apply some Lie symmetry methods to that. Okay, but as I'll tell you, I'm not so smart with the Lie symmetries. What we usually do, we make our lives even simpler. We say, well, what is a physically suitable potential? We usually choose one of these potentials, the B, and there are some suitable types of potentials and sets for that, which are physically viable. So we make our lives super simple. We put in a form for B and it's dead easy. Out pops the other metric function A. And once we've got A and B, the problem is essentially solved. Okay, so this is, I haven't gone into any higher dimensions yet, but it is coming. So the actual first solution, and it is quite an important solution of the Einstein field equations, which was already done, I think around 1916, 1919, was during the First World War by Carl Schwarzschild. It's known as the Schwarzschild solution. So if one puts the matter content, what I had, the T mu nu, firstly make it 0, the vacuum solution, one can actually then solve this thing, the Einstein field equations, and obtain what's called the Schwarzschild solution. And this is actually suitable when you look at, if you introduce a matter content, you can actually use this thing to describe an object like a black hole. And one can see that when certainly in the denominator here, when the RS and the R are equivalent, you're going to get a singularity there, and that's called like a Schwarzschild radius, and that's now associated with, say, an event horizon of say an object like a black hole. And so we would use, say, in a system where there is no external radiation, in a static system, we would use the Schwarzschild metric as the exterior part, so that we can do matching with the interior. So this is very useful to us for our static model. Right, so they now go on to some high dimensional stuff. Now, sort of in the later part of the 20th century, now people have tried to now extend the field equations into higher dimensions. So instead of the 4-dimensional space-time, we can try to look at, say, one higher dimension. But now that can upset certain things here that I'd like to point out. This SD minus 2, that is actually, it's actually an area of a unitary hypersphere. So in GR, in 4 dimensions, this actually worked out to be 8 pi. But now when we extend it into 5 dimensions, when you do this little thing here, it actually becomes something like a 3 pi squared. So it's no longer, the coupling constant has changed. Then this is now a sort of another extension of the high dimensional gravity. This is the so-called Einstein-Gauss-Bonnet. And you see people have played games here. They've added some extra term. There's the coupling constant. So I'm working in 5 dimensions. And this is actually quite a complicated object in terms of the Riemann tensor, the Ricci tensor, and scalar. And I didn't go very carefully into this. I mean, it's really complicated, but I'm just looking at the output of that. And this is basically the output of the Gauss-Bonnet system in 5D. So the field equations now look like that. And this is now a 5D metric. So no longer have I just got, that would be my A squared, my B squared. And this is in the Schwarzschild coordinates, but now I've got something extra here in the higher dimension. And so I'm trying to rationalize how do we navigate in a 5D space? So, I mean, when you try to work with these things, it can become tricky. Quite often we do some kind of transformation to make things look a little bit simpler. And then quite often what we do if we're working with a static system, we invoke something called an equation of state, where we can relate the density and the pressure. But now how does one work with an equation of state in a higher dimension? So this is what disturbed me a little bit. You know, can you say that something in 4 dimensions, you might have a simple linear equation of state, but now would that be the same in a higher dimension? So what I did is I looked at something, just a very simple way to say, well, how do I go from one dimension to another dimension? Can't I just do a simple compactification of that? So I introduced, this is the new part, then I've introduced something called this compactification radius, such that I can navigate, say, from the 5D density to the 4D spacetime. And I've put in here the row 3, excuse me. I've put in the row 3, but that's just symbolic of the 3-dimensional space plus 1 extra time coordinate. So this is actually my 4-dimensional space-time, and this is the 5-dimensional. So can I make any progress with that? And the reason why I want to do that is that I'm interested in the end of the day in getting a model. I want to plot graphs, and I want to say, what is physical here? Say from a 5D system. So can I somehow compare my 5-dimensional fields with, say, something like a 4-dimensional general relativity? So I played some games with this, and I said, well, if I make the alpha 0, I want to try to describe where it was over here. If I make this alpha, which is the Gauss-Bonnet coupling constant 0, can I get back to general relativity, not only in 5 dimensions, but in 4-dimensional space that is something meaningful to us? So then I did just a simple, it's really very simple. I said, what happens at alpha when it's 0? And I get something actually pretty simple that allows me to navigate now from the 5-dimensional to the 4-dimensional space-time. And then I was then concerned, well, why does this, I evaluated it alpha equal to 0. What if we're not at alpha equal to 0? Maybe it is alpha dependent. So I wasn't too sure what to do. So I said, well, let me just at least try to do a basic first order expansion of that, assuming some product here with the epsilon, that hopefully epsilon would be much less than 1. So that at least I'm working to first order there. And I investigated this. Oh, I think I didn't say too much about this up here. This is the equation of state that I will be using. And this type of equation of state is and this again, this is in the 3 space plus 1 extra time coordinate. But you see, this is something physical. So that's why I'm concerned that I need to transform from the 5 dimensions to the 4-dimensional space-time. And this is one of the more sophisticated equations of states because it does refer to the microphysics of the system, because we like to study ultra compact objects like neutron stars. So we at the nuclear saturation density, and these parameters, the ms and the delta, they relate to the microphysics of the system. So this is already a part of particle physics, in fact. So we will make use of that in order to link up the field equations and hopefully then solve for the unknown potential. So here it is. This is obtaining now the gravitational potentials. By using that equation of state, I can then, in the new system of coordinates, I can solve for the remaining gravitational potential, which is the coefficient of the change of time coordinates. And then inside, I've got parameters which I can then give values to, which come from the microphysics, the psi and the gamma. And then, like I say, we try to keep things a little bit simple just so that it makes physical sense. And this is a very, very simple potential, but it's useful, easy to work with, called a Finchley ansatz. So this is the one potential, which is already in here. And then we can easily, very quickly work out the remaining potential. And then we mustn't forget, we need to also make sure that the interior metric is matched to the exterior metric in 5 dimensions. It's something called a Bulwa-Dessa solution, where this function, the metric function in this case is given by this object here, where I must point out M is a 5-dimensional mass. And what we often do in general relativity is we take things like length and time and mass, and we give them all the same unit. And the reason why we can do that is because we do things like we set the speed of light to 1. Not just 1, but the units. So the m over s, the meter per second, is 1. And we take Newton's constant, g, and we set it to 1. That's what general relativity, people working general relativity do. So when you do that, you work with, say, a mass is no longer a mass in kilograms. It becomes a mass in kilometers. So you might say the mass of the sun is, it's not 1 solar mass unit. You work it in terms of kilometers, it might be 1,4. Okay, because it becomes related to the Schwarzschild radius of the sun. And so if you look here at this mass, if you look at the units here, r is a radius, c is just a constant, no, it's a curvature, but it has units of, would have units of, say, kilometers to the -2. And here you've got a r to the 4. So you can immediately see the mass in this 5D mass does not have units of kilometers, it has units of kilometers squared. How do I work with that? And what does it mean? So, and one can see it also from here, that the mass has to be kilometers squared because the coupling constant is, in fact, has to be kilometers to the -2. But you can ask me later about that to verify that if necessary.
Is this the coupling constant of the log?
This is the coupling constant in the Gauss-Bonnet, yeah. So I'm very sensitive to the units, and I need to keep track of that if I eventually want to plot some graphs for my model. So, right. Okay, so now what I want to do is I want to solve my field equations in 5D space, but then I want to reduce them back to the 3 dimensions of space. I know it's a bit confusing because it's actually 4D space-time, but this is something physical. This is something I can work with. And you can see I've got my 8 pi back from the GR equation. So I'm feeling a little bit more comfortable here. And I can take this and I can then start to do some plots and see how does this compare with general relativity. And there's my equations of state, again, in the 4D space-time. So that's workable. And this would be a tangential pressure. So now here's the thing. You see, when I want to work out a mass in 4D space-time, this is the type of integral one would do. One would integrate your density with multiplication here with the r squared. This is a normal thing to get a mass from a density. But when you work in 5 dimensions, it's a little bit different. So now you've got to the power of R3. That's why you raise your units from kilometer to kilometer squared. So I'm thinking, well, can I compare? And it just so happens, I mean, if I take my 5D mass and I divide it by the diameter of my object, I get exactly the right answer. I get my mass again of my compact object in my 4D spacetime. So by assuming this something very simple, then I can quickly do a comparison and I can work out the remaining parameter that I need to complete everything, this little epsilon. it works out pretty easily from that. And then everything is known, and I can then do some calculations. I can compare, say, the physical properties for some objects, say 9.5 kilometers radius, which is what neutron stars are. And the B is a vacuum energy, the S and the delta, these are all so-called quark parameters of the matter content. And then I can see something physical. I can play with the alpha, and I see as I increase the value of the alpha, sorry, the alpha is in, I hope I got this right, kilometers squared. Make a mistake there, yeah. And then the masses, the M circle here is just one, the solar mass of the sun. So we're working at 1.5, say, masses of the sun, and this is what neutron stars are very compact objects which are only maybe not more than 20 kilometers in diameter. And then I change the value of the alpha, and I see how does this affect the mass? How does it affect the central densities? Because we're working at ultra high densities, very, very high, near the nuclear saturation points. How does it affect the pressures? And these are some plots. And I was right with my parameter epsilon. It is much less than 1, so that I satisfy my first order expansion. And then these are my results. This is what, in my mind, this is what the Einstein-Gauss-Bonnet coupling constant does. It actually lowers, it actually lowers the density. And I've seen papers in which it's the exact opposite. I mean, why would it increase? Because I see it as the extra dimension, although we don't have access to it. It helps to relieve the pressure. It helps to reduce that. It's a way for the matter to escape, I would imagine. Because another thing is we're working at, I don't know if you know some physics, but in the MeVs per cubic femtometer here, at 900 MeV per cubic femtometer, you're actually approaching the energies of the proton and the neutron. You're approaching that saturation. So one must be careful here. You know, if you go too high, you know, can you still have that type of material? So that's some results. And one can then look at the pressures. The same thing with the pressures. It seems that it helped to reduce the pressures a little bit. The tangential pressures behaved a bit unusually. And then finally, we did a mass radius plot, which is quite important to gauge the success of our model. And these red dots are actually points, measurements of actual compact stellar objects. So that was my work. And finally, you see, this was a 2019 paper in a European journal, Physical Journal C. So this is why I initiated this whole thing. I struggled to see now, how does the Einstein-Gauss-Bonnet, again, is the alpha, the coupling constant. Why is there such a offset from GR? And in the pressures too. And so that's it.
Questions for the last questions?
I'm sorry, it was not many differential equations to solve, but yeah. Okay. Sorry, it is a physics.
Talk about future work.
Well, the future work is
The actual problem.
well, another thing is, you know, when I tried to put this into EPJC, they were not happy with the simplicity that I had there. They said, well, when you've done your reduction or compactification, does it still survive to be an Einstein-Gauss-Bonnet theory? That was their comment. And I couldn't prove this from the fundamental point of view. So this is more from an analysis aspect, really. Yeah.
I have a
So, okay.
Yeah, what
Yeah.
is the motivation for adding the Gauss-Bonnet term in 5 dimensions? You can add lots of terms.
Well, it seems,
Why not?
well, this Gauss-Bonnet in 5 dimensions,
Right?
It's, yeah,
Lovelock's theory is
Yes.
the simpler extension of the next extension of general relativity is a second order theory of gravity higher dimension. In the fourth dimension, reduced GR. The log of the Gauss-Bonnet term is the first correction term after the Ritz scalar, where in the fourth dimension it's a total boundary term.
Yeah.
So it's the first correction of GR in higher dimension. That's why they consider it. Introduce it.
and it's got some good behavior, but from what I've heard, and I haven't investigated properly yet, it's well behaved. There's a quadratic term in the Lagrangian that is well behaved.
It's a gravity game.
But in what sense it's the simplest?
It's the simplest thing. Yes, modify
In what
the
sense?
general relativity in the most simple thing to drive the dynamics.
And in what sense is it simple? Like, why can add R squared? You're gonna tell me that's not simple.
You can add whatever you want, but
Right.
if you want to use
My
topological,
question is what's simple,
it's the simple introduction of the topological invariant.
but it's only topological in four
Yes.
dimensions. So why are you using it in 5 dimensions?
It's the first term of the Lovelock gravity. I mean, the Lovelock gravity is a series of different invariants.
Gravity, I mean, why not add R squared? I don't understand the whole motivation. Why focus on this one particular?
But it's the first term of the series. The Ritz scalar is the first.
Series of what?
Lovelock gravity, the Lagrangian of Lovelock gravity, it's a series of different invariants. The first term is the Ritz scalar.
Okay, okay.
We have GR. The second term is the Gauss-Bonnet term.
Okay.
Then we have high orders,
Yeah.
which they provide extra non-linear
Invariants.
terms. So, yes. So by using the Gauss-Bonnet term is the simplest thing. By extending general relativity step by step.
Doesn't really answer my question, but thank you.
Okay.
Like, I still don't see that. You're talking about physics.
Yeah.
You're very physical.
Well,
So my
yeah.
question is in physics, what is the physical motivation for adding the Gauss-Bonnet term? So your answer is, well, in 4 dimensions, which is
Well, I think-
5, in 4
yeah.
dimensions, it's topological and doesn't matter. Well, I don't see any physics in any of that. So,
well, GR has some pathologies, I think, associated with it. And I think people try to look for modified theories to overcome those. So
it's just one
it's
attempt.
It's one of the.
it's such an attempt.
One
Yeah.
attempt,
Yeah.
One of
So,
the.
All right. So there's no
Nice.
physics, it's just one attempt.
that's an attempt, yeah.
Infinitely many you can
Yeah,
choose.
I mean, there's things called F of Q gravity and all kinds of things that people just try and they say, well, does it give me something physically meaningful? Out of the Einstein field equations, you can get many solutions which are non-physical. So you really have to take care when you get a solution, does it make sense?
This one's
Yeah,
still
as well.
second order. And
Yes, Lovelock is second order.
That's,
That is the important
that's
stuff.
probably the strongest reason.
Yes,
for doing it.
yes.
Because it's still second order.
And they're not ghosts, I mean, they're
These
not
F of
instabilities.
Q's become higher order and then we don't know.
Yeah.
what-
Yes. They're not instabilities, and that's the important
Yeah.
stuff. Robert, I have a comment. Is there any other comment? Okay. I have a comment. I have a disagreement with the way you defined the energy density that you define a new parameter lambda. L, sorry. function L.
The rate compactification.
Yes.
Yes. There.
Okay.
Um,
Okay, by using these expressions, using that equation of state parameter, it's like you consider that you have an equation of parameter like this, where you can replace directly here the 4 terms.
yeah.
So you have lambda L here, LC,
Mm.
and you have a new equation of state parameter inspired by this.
Yeah.
However, I don't know if this is I will not say that this is the GR energy density, in the sense that you should write, in order to define the GR energy density, you should write the metric in the bulk form, in a form which will be 4 plus 1. So you should consider and separate the bulk.
Yeah.
So this is a bulk fluid. It's not the whole fluid. It's not a GR fluid, it's a bulk.
Yeah.
So probably that's the reason that you see the degrees in your final diagrams.
Yeah.
I mean,
Yeah.
there's no reason to introduce that function here. And another problem is that if you change coordinates,
Yeah.
Because if you take the 5-dimensional metric and you write it like 4 + 1, which is the 1? I mean, from the 3-dimensional space of constant curvature that you have, which is the 1? So that's why you should write in the form of a bulk.
Yeah.
So
Okay.
just in a comment.
Yeah. But I've just seen there wasn't a paper. This was also I mean, this is kind of inspired from like a basic graduate book in, say, string theory, you know, how to convert dimensions, firstly. And secondly, I actually did see something in an article, didn't put the reference there, but when they do convert from one dimension to another, you have to divide or multiply by some kind of volume element. So the nature of that volume element then needs to be investigated more carefully.
Okay.
I think, yeah.
So let's think through
Yeah,
again.